Space and Science News with James. Welcome to our channel. Today, we'll be talking about the incredible discovery of rogue worlds spotted by the James Webb Space Telescope. These fascinating celestial objects, untethered from any star's gravity, are reshaping our understanding of how planets and stars form in the universe, because why not? With groundbreaking insights into the very nature of cosmic creation, this discovery opens up exciting possibilities for future research and exploration. So, let's dive deep into the subject of rogue worlds and uncover the mysteries they hold. In this video, we're exploring a remarkable discovery made by the James Webb Space Telescope, the identification of 6 rogue worlds. These intriguing celestial objects, which are not bound to any star's gravity, have been found within the NGC 1333 nebula, located about 960 light-years from Earth. Among them is the lightest rogue world ever discovered, complete with a dusty disk that hints at its formation process. We'll discuss how these rogue worlds challenge our understanding of cosmic formation, providing insights into the processes that create both stars and planets. Join us as we delve into the details of this groundbreaking research, the implications for our knowledge of the universe, and what these findings mean for the future of astronomy. Get ready to journey into the depths of space and uncover the mysteries of these fascinating cosmic wanderers. The team of astronomers used the incredible capabilities of the James Webb Space Telescope to peer into the young nebula NGC 1333, located about 1,000 light-years away in the Perseus constellation. This star-forming cluster provided the perfect backdrop for their groundbreaking discovery. In their deep survey of NGC 1333, they uncovered 6 objects with masses ranging from 5 to 10 times that of Jupiter. These gas giants represent some of the lowest mass objects ever found that formed through processes typically associated with star formation. What's particularly fascinating is that the telescope detected no objects smaller than 5 Jupiter masses, despite its ability to find them. This absence suggests that objects below this threshold are more likely to form through planetary processes rather than stellar ones. The lightest rogue world identified in this groundbreaking study has a mass equivalent to about 5 Jupiters or 1,600 Earths, making it a truly remarkable celestial object. This planetary mass body is particularly intriguing due to the presence of a dusty disk surrounding it, a characteristic typically associated with the early stages of star formation. The disk, composed of gas and dust particles, is a telltale sign of the object's origins and potential future development. In traditional star formation scenarios, such disks serve as the birthplaces of planets, moons, and other celestial bodies. The presence of this disk around a rogue world of this size is unprecedented and challenges our current understanding of how these objects form and evolve. This discovery suggests that even objects at the lower end of the mass spectrum for star-like formation can maintain these formative structures, potentially allowing for complex systems to develop around them despite their relatively small size and lack of a host star. The researchers embarked on this study with a fundamental question in astronomy at the forefront of their minds: how light can an object be and still form like a star? This query strikes at the heart of our understanding of celestial object formation and the boundaries between different types of cosmic bodies. By utilizing the unprecedented sensitivity and resolution of the James Webb Space Telescope, the team was able to probe deeper into this cosmic conundrum than ever before. Their findings have shed new light on the intricate processes of star and planet formation, suggesting that these two phenomena may be more closely intertwined than previously believed. The discovery of these rogue worlds, particularly the lightest one with its dusty disk, indicates that there might be a continuum rather than a clear-cut distinction between star formation and planet formation mechanisms. This overlap challenges the traditional view of a strict dichotomy between stars and planets. It suggests that nature may employ a spectrum of formation processes, with some objects straddling the line between what we typically classify as stars and planets. The implications of this are far-reaching, potentially requiring astronomers to rethink the categories and definitions they use to classify celestial objects. Moreover, the study highlights the complexity of the universe and the limitations of our current models. It underscores the need for continued exploration and the importance of advanced technologies like the James Webb Space Telescope in pushing the boundaries of our knowledge. By probing the lower mass limits of star-like formation, the researchers are not only answering long-standing questions but also opening up new avenues of inquiry that could reshape our understanding of the cosmos. This groundbreaking discovery has profound implications for our understanding of how stars and planets form, challenging long-held beliefs and opening up new avenues of research in astrophysics. The findings confirm that nature is more versatile than previously thought, producing planetary mass objects through at least two distinct mechanisms, each with its own fascinating characteristics and implications. The first method, which has been well established in astronomical theory, involves the contraction of vast clouds of gas and dust. This process, driven by gravity, is typically associated with star formation. As these cosmic clouds collapse under their own weight, they become denser and hotter, eventually reaching the critical point where nuclear fusion ignites, giving birth to a star. However, this discovery suggests that this same process can also result in objects of much lower mass, blurring the line between stars and planets. The second method occurs within the protoplanetary disks that surround young stars. These disks, composed of gas and dust, are the birthplaces of planets in solar systems like our own. Jupiter, for instance, is believed to have formed through the accumulation of material within such a disk around our young Sunday. The discovery of rogue worlds with similar masses to giant planets, yet formed through star-like processes, suggests a convergence of these two formation mechanisms. The presence of these rogue worlds in the mass range between planets and brown dwarfs is particularly intriguing. Brown dwarfs, often described as failed stars, are objects too massive to be considered planets but not massive enough to sustain hydrogen fusion in their cores. The discovery of objects in this intermediate mass range suggests a continuum of formation processes rather than distinct categories. This blurring of lines challenges our current classification system and hints at a more complex and interconnected universe than previously imagined. Perhaps one of the most exciting aspects of this discovery is the dusty disk observed around the lightest rogue world. This feature, typically associated with young stars and planet formation, raises the tantalizing possibility that these small, star-like objects might be capable of forming their own planetary systems. If this proves to be the case, we may need to expand our search for potentially habitable worlds to include these miniature systems, dramatically increasing the number of places where life could potentially exist in the universe. The implications of this discovery extend far beyond mere classification issues. It forces scientists to rethink existing models of star and planet formation, encouraging a more holistic approach to understanding these processes. The traditional view of a clear distinction between star formation and planet formation may need to be replaced with a more nuanced understanding of a spectrum of formation mechanisms. This finding also highlights the importance of continued exploration and the development of advanced observational technologies. Without the unprecedented sensitivity of the James Webb Space Telescope, these rogue worlds might have remained hidden from view, their secrets locked away in the vast expanse of space. As scientists continue to analyze these findings and conduct follow-up observations, we can expect a wealth of new insights into the fundamental processes that shape our universe. This discovery serves as a reminder of how much we still have to learn about the cosmos and the importance of keeping an open mind as we explore the frontiers of astronomical research. The discovery of rogue worlds and their formation mechanisms represents a significant leap forward in our understanding of the universe. It challenges existing paradigms, opens up new areas of research, and reminds us of the incredible diversity and complexity of cosmic processes. As we continue to unravel these mysteries, we move closer to a more complete and nuanced understanding of our place in the vast tapestry of the cosmos. The discovery of these rogue worlds has opened up a treasure trove of exciting avenues for future research, promising to revolutionize our understanding of planetary formation and the diversity of celestial objects in our universe. In the coming months, the research team plans to embark on an ambitious study of the atmospheres of these faint objects, delving deeper into their composition and origins. This atmospheric analysis will be particularly fascinating as it will allow scientists to compare these rogue worlds to their more familiar counterparts, heavier brown dwarfs and gas giant planets. By examining the spectral signatures of these objects' atmospheres, researchers hope to gain insights into their chemical makeup, temperature profiles, and potential weather patterns. This comparative study could reveal crucial information about how these objects form and evolve in the absence of a host star. It may also shed light on the similarities and differences between rogue worlds and traditional planets, potentially redefining our understanding of what constitutes a planet. The team's success in securing additional observation time with the Webb telescope highlights the importance of their initial findings. This extended research period will focus on exploring similar objects with dusty disks, a characteristic that has piqued the interest of astronomers worldwide. The presence of these disks around rogue worlds opens up the tantalizing possibility of mini-planetary systems forming in these unlikely environments. Imagine a scenario where a rogue world, drifting through the vast emptiness of space, becomes the center of its own miniature solar system. This concept, while speculative, is not entirely far-fetched given our observations of the complex moon systems around Jupiter and Saturn. The researchers aim to investigate whether these dusty disks could coalesce into smaller bodies, perhaps even Earth-sized moons, orbiting these wandering worlds. While the possibility of life as we know it existing on these rogue worlds remains slim due to the lack of a stable energy source like a star, the potential formation of mini-planetary systems adds an intriguing dimension to our search for potentially habitable environments. Could these systems harbor worlds with subsurface oceans, kept liquid by tidal heating, similar to some of the moons in our own solar system? While highly speculative, such possibilities expand our understanding of where life might potentially exist in the universe. The broader implications of this discovery for our understanding of the Milky Way galaxy are profound. The new data suggesting that rogue worlds account for about 10% of celestial bodies in the targeted star cluster is a game-changer. This unexpectedly high percentage challenges our previous assumptions about the rarity of these objects and suggests that our galaxy could be teeming with wandering worlds. If this percentage holds true across other regions of the Milky Way, we may need to significantly revise our estimates of the total number of planets in our galaxy. This could have far-reaching consequences for our models of planetary formation and galactic evolution. It also raises intriguing questions about the role these rogue worlds might play in the broader cosmic ecosystem. Could they, for instance, act as cosmic transporters, carrying organic molecules or even microbial life between star systems? As we reflect on the implications of this discovery, it's impossible to overstate the importance of advanced technology like the Webb Telescope in revolutionizing our understanding of the universe. This powerful instrument, with its unprecedented ability to peer into the depths of space with remarkable clarity, is uncovering phenomena that challenge our long-held assumptions about cosmic processes. The detection of these rogue worlds and their unexpected abundance is a prime example of how new observational capabilities can lead to paradigm-shifting discoveries. It underscores the importance of continued investment in cutting-edge astronomical instruments and the need for an open-minded approach to interpreting the data they provide. This research also stands as a shining example of the power of international cooperation in advancing our knowledge of the cosmos. The James Webb Space Telescope itself is a product of collaboration between NASA, the European Space Agency, and the Canadian Space Agency. The research team, comprised of scientists from various institutions and countries, further exemplifies how global scientific cooperation can lead to groundbreaking discoveries. As we continue to explore the universe, discoveries like these serve as poignant reminders of the vast mysteries that still await us. They inspire us to keep pushing the boundaries of our knowledge, to remain curious, and to never stop questioning our assumptions about the nature of the cosmos. Looking to the future, we can anticipate a wealth of groundbreaking discoveries from the Webb Telescope and other advanced instruments on the horizon. These tools will continue to illuminate the processes that shape our universe, from the formation of the first stars and galaxies to the evolution of planetary systems like our own. The journey of cosmic exploration is far from over. Each new discovery, like these rogue worlds, opens up new questions and avenues for research. As we continue to look up at the night sky, we are reminded of the incredible vastness and complexity of the universe we inhabit. Who knows what other incredible discoveries await us in the vast expanse of space? The only certainty is that our cosmic journey of discovery is just beginning, and the universe still has many secrets to reveal. And with that, we conclude our journey into the fascinating world of rogue planets discovered by the James Webb Space Telescope. These celestial wanderers, drifting freely through space, have opened up a new chapter in our understanding of planetary and stellar formation. From the lightest rogue world with its intriguing dusty disk to the implications for many planetary systems, each discovery pushes the boundaries of our cosmic knowledge. These findings not only challenge our current theories but also inspire new questions about the diversity of objects in our universe. As we've seen, the line between planets and stars is becoming increasingly blurred, reminding us of the complex and interconnected nature of cosmic processes. The James Webb Space Telescope continues to be a game-changer, allowing us to peer deeper into space and time than ever before. Thank you for joining us on this cosmic adventure. Your curiosity and interest in these groundbreaking discoveries fuel our passion for sharing the wonders of the universe. As we eagerly await future observations and discoveries, let's continue to look up at the night sky with wonder and appreciation for the vast, mysterious cosmos we're all a part of. Until next time, keep exploring, keep questioning, and keep marveling at the incredible universe we call home. Imagine gazing into the depths of space and seeing a question mark. Not just any question mark, but one spanning billions of light years, formed by entire galaxies. Sounds like science fiction. Well, buckle up, because this cosmic punctuation is very real, and it's about to blow your mind. Today, we'll be talking about the cosmic question mark, because why not explore one of the most bizarre and fascinating discoveries in recent astronomy? This celestial enigma isn't just a quirky shape in the sky. It's a window into our galaxy's past, a cosmic time machine that could rewrite our understanding of the universe. But here's where it gets really interesting. This galactic question mark might hold the key to unlocking secrets about our own Milky Way's teenage years. Imagine seeing your galaxy's awkward phase from billions of years ago. That's exactly what we're dealing with here. And if you think that's mind-bending, wait until you hear how this discovery is challenging everything we thought we knew about galaxy formation and evolution. Are you ready to have your cosmic mind blown? Let's dive deep into the subject of the cosmic question mark and unravel the mysteries of our universe. In the vast expanse of our universe, galaxies come in all shapes and sizes. But have you ever imagined a galaxy shaped like a question mark? That's exactly what astronomers have discovered using NASA's James Webb Space Telescope. This cosmic question mark isn't just a quirky celestial formation, it's a window into our galaxy's past, offering clues about what the Milky Way might have looked like billions of years ago. Today, we're going to embark on a journey through time and space, exploring this fascinating discovery and what it tells us about galaxy formation, star birth, and the evolution of our cosmic neighborhood. We'll delve into the cutting-edge technology that made this observation possible and unravel the mysteries hidden in this celestial punctuation mark. So, fasten your seatbelts and prepare for a mind-bending adventure as we explore the cosmic question mark and its implications for our understanding. Let's start by taking a closer look at this intriguing cosmic formation. The question mark shape isn't a single galaxy, but rather a combination of two interacting galaxies that have been distorted and magnified by a phenomenon known as gravitational lensing. This fascinating effect occurs when the immense gravity of a massive object, like a galaxy cluster, bends and magnifies the light from more distant objects behind it. In this case, the galaxy cluster max, J0417.5-1154 acts as a cosmic magnifying glass, allowing us to see enhanced details of the distant galaxies that form our cosmic question mark. The question mark itself consists of two main components. The curved part is formed by a dusty red galaxy that was previously invisible to other telescopes like Hubble. It only came into view thanks to Webb's ability to detect infrared light. The dot that completes the question mark is an unrelated galaxy that happens to be in the right place from our perspective. What's particularly exciting about this discovery is its rarity. Astronomers know of only 3 or 4 similar gravitational lens configurations in the observable universe. This makes the cosmic question mark a valuable find, showcasing the power of the James Webb Space Telescope and hinting at the possibility of discovering more such configurations in the future. The unique alignment that creates this question mark shape is called a hyperbolic umbilic gravitational lens. This rare configuration results in 5 images of the galaxy pair seen in Webb's image, 4 of which trace the top of the question mark. This cosmic question mark isn't just a pretty picture, it's a treasure trove of information about galaxy formation and evolution. By studying these distorted and magnified galaxies, astronomers can peer back in time to when the universe was much younger, giving us insights into the early stages of galaxy development. The discovery of the cosmic question mark wouldn't have been possible without the James Webb Space Telescope, JWST. Launched in December 2021, Webb is the most powerful space telescope ever built, designed to peer further into space and time than any of its predecessors. What makes Webb so special is its ability to observe in infrared light, allowing it to see through cosmic dust that obscures visible light. This is how it was able to detect the dusty red galaxy that forms part of our cosmic question mark. With a primary mirror measuring 6.5 meters in diameter, Webb has a much larger light collecting area than Hubble, enabling it to see fainter, more distant objects. Additionally, Webb orbits the Sun about 1.5 million kilometers from Earth at a special location known as the second Lagrange point, L2. This unique position keeps it cold and stable, making it ideal for infrared observations. The cosmic question mark discovery showcases Webb's capabilities perfectly. While the Hubble Space Telescope had previously observed this region, it couldn't detect the dusty red galaxy that forms the curved part of the question mark. The longer wavelengths of infrared light that Webb can detect were able to pass through the cosmic dust, revealing this hidden galaxy. Moreover, Webb's near-infrared imager and slitless spectrograph, NIRIS, instrument allowed astronomers to detect star formation locations within galaxies billions of light-years away. This level of detail in such distant objects was previously impossible to achieve. The James Webb Space Telescope is not just about pretty pictures, it's a revolutionary tool that's changing our understanding of the universe. By peering further back in time and seeing through cosmic dust, Webb is helping us unravel the mysteries of galaxy formation, star birth, and the early universe. Now that we understand how the cosmic question mark was discovered, let's dive into what it tells us about galaxy formation and evolution. The two main galaxies forming the question mark are located about 7 billion light-years away from Earth. This means we're seeing them as they were 7 billion years ago, when the universe was about half its current age. From studying these galaxies, astronomers have learned that they are likely in the early stages of interacting with each other. While their shapes aren't too disrupted yet, there are signs that their gravitational forces are beginning to affect each other. Both galaxies show active star formation in several compact regions, likely a result of gas from the two galaxies colliding, triggering the birth of new stars. The red color of one galaxy indicates it's rich in cosmic dust, which can obscure visible light but is transparent to the infrared light that Webb detects. These galaxies are similar in mass to what our Milky Way would have been at that time in cosmic history. This gives us a glimpse into what our own galaxy might have looked like in its teenage years. The cosmic question mark is more than just an interesting shape, it's a laboratory for studying galaxy evolution. By observing galaxies at different stages of their lives and in different environments, astronomers can piece together the story of how galaxies grow and change over billions of years. This discovery also highlights the importance of gravitational lensing in astronomy. Without this cosmic magnifying effect, these distant galaxies would be too faint and small for us to study in detail. Gravitational lenses like this one allow us to push the boundaries of what we can observe, peering further back in time and space than ever before. One of the most exciting aspects of the cosmic question mark discovery is what it tells us about our own galaxy's history. The Milky Way, like all galaxies, has evolved over billions of years. But how can we study its past? The answer lies in looking at distant galaxies like those in the cosmic question mark. These galaxies, seen as they were billions of years ago, are similar in mass to what the Milky Way would have been at that time. They serve as a kind of galactic time machine, allowing us to study what our galaxy's teenage years might have been like. The Milky Way began forming very early in the universe's history, with its oldest stars dating back to about 13 billion years ago. Between 11 and 7 billion years ago, the Milky Way went through a period of intense star formation, building up about 90% of its stars during this time. The Milky Way grew not just through star formation, but also by merging with and absorbing smaller galaxies. The flat disk structure of the Milky Way, where most of its younger stars, including our Sun, are found, formed gradually over billions of years. By studying galaxies like those in the cosmic question mark, astronomers can fill in the gaps in our understanding of the Milky Way's history. They can see how galaxies of similar mass behave, how they form stars, and how they interact with their neighbors. This research doesn't just satisfy our curiosity about our cosmic home, it helps us understand fundamental processes of galaxy formation and evolution. By learning about our galaxy's past, we gain insights into the forces that shape galaxies throughout the universe. The discovery of the cosmic question mark is just the beginning. As we continue to explore the universe with powerful tools like the James Webb Space Telescope, we're entering a new era of what astronomers call galactic archaeology. This field involves the study of the structure, dynamics, and evolution of galaxies by examining their constituent stars, similar to how archaeologists study human history by examining artifacts. By studying the ages and chemical compositions of stars in different parts of galaxies, astronomers can reconstruct their formation history. Evidence of past mergers can be found in the motions and compositions of stars, helping us understand how galaxies grow over time. The motions of stars and gas can reveal the distribution of invisible dark matter in and around galaxies. Additionally, by examining stars of different ages, astronomers can piece together how star formation rates have changed over a galaxy's lifetime. The James Webb Space Telescope is a game-changer for this field. Its ability to see through cosmic dust and observe extremely distant galaxies is providing unprecedented data for galactic archaeologists. Looking ahead, we can expect many more discoveries like the cosmic question mark. Each new observation helps us refine our models of galaxy formation and evolution, bringing us closer to a complete understanding of our cosmic history. Moreover, these studies have implications beyond astronomy. By understanding how galaxies form and evolve, we gain insights into the fundamental physics that governs our universe. We learn about the interplay between gravity, dark matter, and the mysterious force known as dark energy that's causing the universe's expansion to accelerate. As we continue to push the boundaries of what we can observe, who knows what other cosmic punctuation marks we might find written across the sky. As we conclude our journey through the cosmic question mark, it's clear that the universe has a flair for the dramatic. Who knew punctuation could be so mind-blowing on a galactic scale? But beyond its quirky shape, this celestial enigma has opened up a treasure trove of insights into the very fabric of our cosmos. Let's recap what we've learned. First, the power of gravitational lensing has once again proven to be an invaluable tool in our astronomical arsenal. It's allowed us to peer deeper into space and time than ever before, giving us a front-row seat to the universe's early days. This cosmic magnifying glass is not just a neat trick, it's revolutionizing our understanding of galaxy formation and evolution. Secondly, the concept of galactic archaeology has taken center stage. By studying these distant, distorted galaxies, we're essentially looking at a snapshot of our own Milky Way's past. It's like finding a cosmic family photo album, showing us what our galactic home looked like in its awkward teenage years. This comparison is invaluable in understanding how galaxies like ours grow and change over billions of years. But perhaps the most profound conclusion we can draw is this: the universe is far more interconnected and dynamic than we ever imagined. The cosmic question mark is a testament to the intricate dance of gravity, dark matter, and the mysterious force we call dark energy. It shows us that even across vast cosmic distances, galaxies interact, shape each other, and tell a collective story of cosmic evolution. As we look to the future, we can be certain that more cosmic wonders await discovery. Each new finding brings us closer to understanding our place in the vast cosmic tapestry, from the birth of the first galaxies to the ultimate fate of our universe. The James Webb Space Telescope and other cutting-edge instruments are opening up new frontiers of exploration, promising even more mind-bending discoveries in the years to come. So, the next time you look up at the night sky, remember, you're not just stargazing. You're witnessing the greatest story ever told, written in starlight across the cosmos. And the best part? We're all part of this cosmic tale, our very atoms forged in the hearts of ancient stars. If you've enjoyed this galactic adventure, don't forget to hit that subscribe button and ring the notification bell. Trust me, you won't want to miss our next voyage into the cosmic unknown. Share this video with your friends and family. Let's spread the wonder of the cosmos far and wide. And leave a comment below telling us what cosmic mystery you'd like us to explore next. Until then, keep looking up and keep questioning. The universe is full of mysteries, and together, we'll unravel them one celestial punctuation mark at a time. Who knows? The next great discovery could be hiding in plain sight, waiting for curious minds like yours to spot it. So stay curious, stay excited, and remember, in the grand cosmic story, you're not just a spectator, you're a vital part of the narrative. Thanks for joining us on this incredible journey through space and time. Until our next cosmic adventure, keep wondering, keep exploring, and keep reaching for the stars. Imagine a galaxy so strange, it's challenging everything we thought we knew about the early universe. A cosmic oddball that's got astronomers scratching their heads and rewriting the textbooks. What if I told you that this galaxy's gas shines brighter than its stars? It sounds impossible, doesn't it? But that's exactly what NASA's James Webb Space Telescope has discovered. A galaxy that breaks all the rules, existing at a time when the universe was still in its infancy. This isn't just another space discovery, it could be the key to unlocking the mysteries of how the very first galaxies formed. Today, we'll be talking about this mind-bending galaxy, GS/NDG 9422, because why not? It's not every day we find something that could be the missing link between the universe's first stars and the galaxies we see today. But here's where it gets really interesting: this discovery might just change everything we thought we knew about the early universe. How? Well, that's what we're about to find out. Let's dive deep into the cosmic mystery of GS/NDG 9422 and uncover the secrets it holds about our universe's past, and maybe even its future. In the vast expanse of the cosmos, our understanding of the universe's early days has long been shrouded in mystery. But now, thanks to NASA's James Webb Space Telescope, we're peering deeper into space and time than ever before. And what we're finding is nothing short of extraordinary. Imagine a galaxy so strange, so unlike anything we've seen before, that it challenges our very understanding of how the universe evolved. This is the story of GS-NDG 9422, a galaxy that might just be the missing link between the universe's first stars and the galaxies we see today. Discovered approximately 1 billion years after the Big Bang, GS-NDG 9422 stands out due to its odd, never-before-seen light signature. Unlike typical galaxies where stars shine brightest, in this cosmic oddball, it's the gas that outshines the stars. This phenomenon, predicted in the environments of the universe's first generation of stars, has never been observed in such detail before. The galaxy's stars are incredibly hot, with temperatures exceeding 140,000 degrees Fahrenheit, 80,000 degrees Celsius, more than twice as hot as typical massive stars in our local universe. These scorching stars are heating the surrounding gas to such extreme temperatures that it glows brighter than the stars themselves. This discovery is not just another dot in the sky, it's a glimpse into a time when the cosmos was still young and chaotic. The light from this galaxy tells us a story about how stars formed, how galaxies evolved, and how our universe became what it is today. As researchers continue to study GS-NDG 9422 and search for similar galaxies, we may be on the brink of rewriting our understanding of the early universe. It all started with a faint dot in Webb's field of view. Just another speck among countless others, you might think. But when astronomers looked closer, they realized they were onto something big, really big. Alex Cameron, a researcher from the University of Oxford, was the first to notice something odd about this galaxy's light. "My first thought in looking at the galaxy's spectrum was, that's weird," he said. And in the world of astronomy, weird often means exciting. So what made this galaxy so strange? It wasn't shining like any galaxy we've seen before. Instead of seeing light from stars, the telescope was picking up something else entirely. The gas in this galaxy was outshining its stars. This revelation opened up a whole new avenue of research. Astronomers began to wonder if this could be a common phenomenon in the early universe or if it was an anomaly. The implications were staggering. If gas could outshine stars in this way, what else might we be missing in our understanding of galactic evolution? To unravel this cosmic mystery, Cameron teamed up with Harley Katz, a theorist specializing in cosmic gas clouds. Together, they dove into computer models, simulating scenarios where extremely hot, massive stars could heat surrounding gas to such intense temperatures that it would glow brighter than the stars themselves. Their findings were astounding. The stars in this galaxy, dubbed GS-NDG 9422, must be incredibly hot, more than 140,000 degrees Fahrenheit. That's about twice as hot as the hottest stars we typically see in our local universe. These scorching stars are heating the surrounding gas to temperatures that make it shine with unprecedented brightness. This discovery isn't just a cosmic curiosity, it's a potential missing link in our understanding of galactic evolution. GS-NDG 9422 exists about 1 billion years after the Big Bang, a time when the universe was still in its infancy. It's not quite like the first generation of stars, known as population 3 stars, but it's also not like the galaxies we're familiar with today. Instead, it seems to be caught in a brief yet intense phase of star formation, a cosmic sweet spot where conditions were just right for creating these extraordinary stellar furnaces. This moment in time captures how galaxies may have transitioned from their primordial states into the more complex structures we see today. As researchers continue to study GS-NDG 9422 and search for similar galaxies, we may be on the brink of rewriting our understanding of the early universe. Each new discovery brings us closer to unraveling the cosmic story of how our universe became what it is today. Now you might be wondering, how can gas shine brighter than stars? It's a good question and one that had astronomers scratching their heads too. To figure it out, Cameron reached out to his colleague Harley Katz, a theorist who knows a thing or two about cosmic gas clouds. Together they started piecing together the puzzle using computer models to simulate what might be happening in this galaxy. What they found was mind-blowing. The stars in this galaxy must be incredibly hot, hotter than anything we've seen in our neck of the woods. We're talking about stars that are more than 140,000 degrees Fahrenheit. That's about twice as hot as the hottest stars we typically see in our local universe. These scorching hot stars are heating up the surrounding gas so much that it's glowing brighter than the stars themselves. This phenomenon could provide vital clues about how galaxies formed during the chaotic period shortly after the Big Bang. The researchers hypothesized that GS NDG 9422 is undergoing an intense phase of star formation within a dense gas cloud, an environment where massive stars are born at an unprecedented rate. As these massive stars emit vast amounts of energy, they bombard their surroundings with photons, light particles, that excite the gas around them to such an extent that it glows intensely. This interaction between hot stars and gas clouds could be more common than we realize in the early universe. The discovery of GS NDG 9422 is not just a cosmic curiosity, it's a potential missing link in our understanding of galactic evolution. This galaxy exists about 1 billion years after the Big Bang, a time when the universe was still in its infancy. It's not quite like the first generation of stars, known as population 3 stars, but it's also not like the galaxies we're familiar with today. Instead, it seems to be caught in a brief yet intense phase of star formation, a cosmic sweet spot where conditions were just right for creating these extraordinary stellar furnaces. This moment in time captures how galaxies may have transitioned from their primordial states into the more complex structures we see today. As researchers continue to study GS NDG 9422 and search for similar galaxies, we may be on the brink of rewriting our understanding of the early universe. Each new discovery brings us closer to unraveling the cosmic story of how our universe became what it is today. But why is this discovery so important? Well, it's giving us a glimpse into a crucial period in the universe's history. You see, GS NDG 9422 exists about 1 billion years after the Big Bang. That might sound like a long time, but in cosmic terms, it's just a blink of an eye. This galaxy could be showing us a missing link in galactic evolution, an intermediary stage between primordial stars and well-established galaxies like our own Milky Way. It's not quite like the first generation of stars known as population 3 stars. We know this because Webb's data shows too much chemical complexity for that classification. Instead, GS NDG 9422 seems to be caught in a brief yet intense phase of star formation, a time when conditions were ripe for creating massive celestial bodies at an unprecedented rate. Imagine a massive cloud of dense gas filled with newly formed stars, hotter and more massive than anything we see today. These stars are pumping out so much energy that they make their entire gas cloud glow like a cosmic light bulb. This moment captures how galaxies transitioned from their primordial states into more complex structures over billions of years. Understanding GS NDG 9422 helps astronomers piece together how galaxies formed and evolved during this chaotic era when everything was still taking shape, a time when gravity pulled matter together to form stars and galaxies from an almost uniform cosmic soup. The discovery of GS NDG 9422 is particularly exciting because it challenges our current models of galaxy formation. Most galaxies we observe are dominated by the light from their stars, but in this case, the gas is outshining the stars. This unusual characteristic suggests that the stars in GS NDG 9422 are incredibly hot and massive, heating the surrounding gas to temperatures we rarely see in the modern universe. This finding could have far-reaching implications for our understanding of the early universe. It suggests that the conditions for star formation in the early cosmos were dramatically different from what we see today. The intense radiation from these hot, massive stars could have played a crucial role in shaping the intergalactic medium and influencing the formation of subsequent generations of stars and galaxies. Moreover, the study of GS NDG 9422 could provide valuable insights into the process of cosmic reionization, a pivotal epoch in the universe's history when the first stars and galaxies ionized the neutral hydrogen that permeated space after the Big Bang. The extreme conditions observed in this galaxy might have been more common in the early universe, potentially contributing significantly to this reionization process. As astronomers continue to study GS NDG 9422 and search for similar galaxies, they hope to build a more complete picture of how the universe evolved from its earliest stages to the complex cosmos we see today. Each discovery like this brings us one step closer to understanding our cosmic origins and the fundamental processes that shape the universe. This discovery is shaking up our understanding of how galaxies formed and evolved in the early universe. It's showing us the conditions were very different from what we see today. Harley Katz explains it well. It looks like these stars must be much hotter and more massive than what we see in the local universe. This makes sense because the early universe was indeed a very different environment, a place where gravity was stronger and matter was denser. But here's where things get even more interesting. Right now, GS-NDG 9422 is just one example among many possibilities yet to be explored. We don't know if this was a common phase most galaxies went through or if it was just an anomaly, a rare occurrence that happened under specific conditions. To figure that out, astronomers need to find more galaxies like GS-NDG 9422 to expand their data set and draw more definitive conclusions about galactic evolution during this crucial period. They're actively searching through Webb's observations for other candidates from around the same time frame, hoping to uncover additional examples that could further illuminate our understanding of cosmic history. The implications extend beyond just one galaxy. They touch upon fundamental questions regarding star formation rates and chemical enrichment processes within galaxies during their formative years. If GS-NDG 9422 is indicative of broader trends among early galaxies, it could reshape our theories about how matter coalesced into larger structures over time. This discovery challenges our current models of galaxy formation and evolution. Most galaxies we observe are dominated by the light from their stars, but in GS-NDG 9422, the gas outshines the stars. This unusual characteristic suggests that the conditions for star formation in the early cosmos were dramatically different from what we see today. The intense radiation from these hot, massive stars could have played a crucial role in shaping the intergalactic medium and influencing the formation of subsequent generations of stars and galaxies. It might have contributed significantly to the process of cosmic reionization, a pivotal epoch in the universe's history when the first stars and galaxies ionized the neutral hydrogen that permeated space after the Big Bang. Moreover, the study of GS-NDG 9422 provides valuable insights into the chemical evolution of the early universe. The presence of complex chemical elements in this galaxy suggests that it has already undergone at least one generation of star formation and supernova explosions, which enriched its interstellar medium with heavier elements. This finding has implications for our understanding of how quickly the first galaxies evolved and how rapidly they produced and dispersed heavy elements throughout the cosmos. It challenges our assumptions about the timescales involved in early galactic chemical evolution and may require us to revise our models of how quickly the universe became enriched with the elements necessary for life as we know it. The discovery of GS-NDG 9422 also highlights the power of the James Webb Space Telescope in revolutionizing our understanding of the early universe. Its ability to detect such faint, distant galaxies with unprecedented clarity is opening up new frontiers in astronomy and cosmology. As we continue to explore the early universe with Webb and other advanced telescopes, we may uncover more galaxies like GS-NDG 9422, each providing a unique piece of the cosmic puzzle. These discoveries will help us build a more complete picture of how the universe evolved from its earliest stages to the complex cosmos we see today. The study of these early galaxies is not just about understanding our cosmic past, it's also about predicting the future of our universe. By understanding how galaxies formed and evolved in the early universe, we can better predict how they will continue to change over cosmic time scales. In conclusion, the discovery of GS-NDG 9422 represents a significant milestone in our quest to understand the early universe. It challenges our existing models, raises new questions, and opens up exciting avenues for future research. As we continue to push the boundaries of our observational capabilities, we can look forward to many more such discoveries that will help us unravel the mysteries of our cosmic origins. And that's exactly what Cameron, Katz, and their team are doing now. They're scouring Webb's data looking for more galaxies from the same time period that might show similar characteristics. It's a very exciting time, Cameron says with enthusiasm. We are just at the beginning of new discoveries and understanding. And he's right. With every new image from Webb, we're pushing back frontiers of knowledge while peering further into cosmic dawns we've never seen before. The hunt involves analyzing spectra, the unique fingerprints left behind by light emitted from distant objects, to identify other candidates exhibiting similar anomalies as GS-NDG 9422. Each new candidate adds another layer to our understanding of how galaxies evolved during those formative years after the Big Bang. As astronomers delve deeper into Webb's treasure trove of data, searching for signs of nebular light outshining starlight, they're not just looking for isolated examples, they're trying to build a comprehensive picture of galactic evolution during this critical epoch. This ongoing research highlights how rapidly our understanding can change with new technology like Webb. It's opening doors we didn't even know existed before. With each new discovery comes fresh questions that will lead us down paths we haven't yet imagined. The search for galaxies similar to GS and DG 9422 is not just about finding more examples, it's about understanding the frequency and conditions under which these unusual galaxies form. Are they common in the early universe, or is GS and DG 9422 a rare cosmic oddity? The answer to this question could have profound implications for our understanding of galaxy formation and evolution. As researchers analyze more data, they're also refining their models and theories. The discovery of GS and DG 9422 has already challenged existing models of galaxy formation, prompting scientists to revisit their assumptions about the early universe. This iterative process of observation, theory, and model refinement is at the heart of scientific progress. The team is also investigating how these galaxies might have influenced their surroundings. The intense radiation from their hot stars and glowing gas could have played a crucial role in reionizing the early universe, a key event in cosmic history that made the universe transparent to ultraviolet light. Moreover, the study of these galaxies provides insights into the chemical evolution of the universe. By analyzing the spectra of these distant objects, astronomers can determine their chemical composition, shedding light on how quickly the first generation of stars enriched the cosmos with heavy elements. The implications of this research extend far beyond astronomy. Understanding the formation and evolution of the first galaxies helps us piece together the story of our cosmic origins. It provides context for the existence of our own galaxy, the Milky Way, and ultimately, our place in the universe. As Webb continues to collect data, astronomers are also looking forward to future missions and technologies that will complement and extend Webb's capabilities. The next generation of ground-based and space-based telescopes will allow us to push even further into the cosmic frontier, potentially revealing the very first stars and galaxies to form after the Big Bang. In the meantime, Cameron, Katz, and their colleagues continue their meticulous work, analyzing data, refining models, and searching for more cosmic oddities like GS and DG 9422. Their work reminds us that the universe is full of surprises, and that our journey of cosmic discovery is far from over. With each new finding, we come a step closer to understanding the grand story of our universe, a story that began nearly 14 billion years ago and continues to unfold to this day. So what does all this mean for our understanding of the universe? Well, it's helping us fill crucial gaps in cosmic storylines. We're starting to see how our universe transitioned from its earliest days with its first generation of stars into rich tapestry filled with diverse galaxies we observe today. This discovery feels like finding missing pages within cosmic history books. It reveals chapters we've never seen before, a time when galaxies were very different from what we recognize today. And who knows what other surprises Webb might have in store for us. With each new discovery unfolding before our eyes, we're rewriting narratives surrounding cosmic evolution while witnessing birth processes behind celestial phenomena previously inaccessible. As we continue exploring deeper realms beyond mere visual limits imposed by previous telescopes, we're gaining insights into structures forming across vast distances throughout spacetime itself. The story surrounding GS and DG 9422 serves as just beginning. It opens up new questions alongside fresh avenues for research while presenting possibilities regarding understanding origins behind cosmic phenomena. As we peer deeper into spacetime fabric, who knows what other wonders await discovery? This discovery is reshaping our understanding of the early universe in profound ways. It suggests that the conditions for star formation in the cosmic dawn were far more extreme than we previously thought. The intense radiation from these hot, massive stars could have played a crucial role in shaping the intergalactic medium and influencing the formation of subsequent generations of stars and galaxies. Moreover, the study of GS and DG 9422 provides valuable insights into the chemical evolution of the early universe. The presence of complex chemical elements in this galaxy suggests that it has already undergone at least one generation of star formation and supernova explosions, which enriched its interstellar medium with heavier elements. This finding has implications for our understanding of how quickly the first galaxies evolved and how rapidly they produced and dispersed heavy elements throughout the cosmos. The discovery also highlights the power of the James Webb Space Telescope in revolutionizing our understanding of the early universe. Its ability to detect such faint, distant galaxies with unprecedented clarity is opening up new frontiers in astronomy and cosmology. As we continue to explore the early universe with Webb and other advanced telescopes, we may uncover more galaxies like GS and DG 9422, each providing a unique piece of the cosmic puzzle. These discoveries are not just about understanding our cosmic past, they're also about predicting the future of our universe. By understanding how galaxies formed and evolved in the early universe, we can better predict how they will continue to change over cosmic time scales. This knowledge could help us understand the ultimate fate of our own galaxy and the universe as a whole. Furthermore, the study of these early galaxies could provide insights into fundamental physics. The extreme conditions present in these early galaxies serve as natural laboratories for testing our theories about how matter behaves under intense gravitational and radiative forces. Any discrepancies between our observations and theoretical predictions could point to new physics beyond our current understanding. The discovery of GS-NDG 9422 also raises intriguing questions about the possibility of life in the early universe. While the intense radiation and frequent supernova explosions in these early galaxies might seem hostile to life as we know it, they also created the heavy elements necessary for complex chemistry. Could life have emerged earlier in cosmic history than we previously thought possible? As we continue to push the boundaries of our observational capabilities, we can look forward to many more discoveries that will help us unravel the mysteries of our cosmic origins. Each new finding brings us closer to answering some of humanity's most profound questions. Where did we come from? How did the universe evolve to its present state? And what does the future hold for our cosmic home? The journey through the cosmic mystery of GS-NDG 9422 reveals that this strange galaxy is more than just a curiosity. It serves as a window into the early universe, shedding light on how the first galaxies might have formed and evolved. This discovery challenges our understanding of galactic evolution, showing us that the early universe was a place of extremes, where stars burned hotter and gas glowed brighter than anything we see in our cosmic neighborhood today. This finding isn't just changing our view of the past, it's reshaping our understanding of how the universe came to be. Perhaps the most exciting aspect is what this means for future research. GS-NDG 9422 is likely just the first of many such galaxies waiting to be discovered. As we continue to explore the deep cosmos with tools like the James Webb Space Telescope, who knows what other cosmic oddities we might uncover. This discovery highlights that the universe is full of surprises. Just when we think we've got it figured out, something comes along to shake up our theories and push our understanding further. It's a testament to human curiosity and the incredible technology we've developed to explore the cosmos. Thank you for joining me on this cosmic journey. If you enjoyed this video and want to stay updated on the latest discoveries in space, don't forget to hit that subscribe button. If you have any thoughts or questions about GS-NDG 9422 or early galaxy formation, leave a comment below. Your question might inspire our next video. Until next time, keep looking up and wondering about the mysteries of our universe. There's always more to discover. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. In the vast expanse of our solar system, a colossal storm has been raging for centuries. Larger than Earth itself, this swirling vortex of gas and wind has captivated astronomers and stargazers alike. But just when we thought we understood this cosmic behemoth, it threw us a curveball. Recent observations have revealed something so unexpected, so bizarre, that it's forcing scientists to rethink everything they knew about planetary weather systems. Today, we're talking about Jupiter's Great Red Spot because why not? This iconic feature of our solar system's largest planet has been hiding secrets that are only now coming to light. What if I told you that this massive storm is behaving in ways that defy explanation? That it's moving and changing in patterns that have left even the most experienced researchers scratching their heads? But hold on to your telescopes, because this story goes far beyond Jupiter. These groundbreaking findings could completely transform our understanding of weather patterns throughout the cosmos. From distant exoplanets to our own backyard, the implications are truly astronomical. So, let's plunge into the swirling enigma of Jupiter's Great Red Spot and unravel the secrets behind its perplexing behavior. The answers we find might just rewrite the books on planetary science as we know it. Jupiter, the largest planet in our solar system, has captivated astronomers for centuries. Its most iconic feature, the Great Red Spot, has been a subject of fascination for over 150 years. This massive storm, large enough to swallow Earth, has been a constant presence in Jupiter's atmosphere, swirling and churning with incredible force. But recent observations from NASA's Hubble Space Telescope have revealed surprising new details about this celestial wonder. In this video, we'll explore the latest discoveries about Jupiter's Great Red Spot and how it's behaving in ways that have astonished even seasoned scientists. From its unexpected movements to its changing size, we'll delve into the mysteries of this colossal storm and what it might tell us about the nature of planetary weather systems, not just in our solar system, but potentially on distant exoplanets as well. The Great Red Spot, an anticyclonic storm located 22 degrees south of Jupiter's equator, produces wind speeds up to 432 km per hour, 268 miles per hour. Its rich red-orange color, whose origin remains unknown, makes it the most recognizable feature on Jupiter. As we embark on this journey to understand one of the most enduring and enigmatic features in our cosmic neighborhood, we'll uncover the latest findings that challenge our previous understanding of this planetary behemoth. From December 2023 to March 2024, the Hubble Space Telescope conducted an intensive 90-day observation campaign focused on Jupiter's Great Red Spot. This unprecedented study has yielded startling results that challenge our understanding of this massive storm system. The high-resolution images captured by Hubble have revealed that the Great Red Spot is far from the stable, unchanging feature we once thought it to be. Instead, it's displaying behavior that can only be described as erratic and unpredictable. The most striking discovery is that the Great Red Spot is oscillating, or jiggling, much like a bowl of gelatin. This movement isn't just a slight wobble, it's a significant fluctuation in both size and shape that occurs over a relatively short period. The storm is literally pulsating, expanding, and contracting in a rhythmic dance that has never been observed before. This behavior is so unusual that scientists currently have no hydrodynamic explanations for it. Amy Simon, a researcher at NASA's Goddard Space Flight Center and lead author of the study, expressed her surprise at these findings. While we knew its motion varies slightly in its longitude, we didn't expect to see the size oscillate, she said. As far as we know, it's not been identified before. This observation was only possible due to Hubble's high-resolution imaging capabilities and the extended duration of the study. The time-lapse movie created from Hubble's images shows the Great Red Spot squeezing in and out while simultaneously speeding up and slowing down. This complex motion pattern is completely unexpected and has left scientists puzzled. The fact that such a massive storm system can change its dimensions so rapidly challenges our current models of planetary atmospheric dynamics. These observations are not just scientifically intriguing, they're visually stunning. The swirling patterns of the Great Red Spot, with its rich reds and oranges set against the striped backdrop of Jupiter's atmosphere, create a mesmerizing spectacle. As we watch the storm pulse and shift, we're witnessing a cosmic dance on a scale that's hard to comprehend, a reminder of the dynamic and ever-changing nature of our universe. The Great Red Spot has been a constant presence on Jupiter for as long as we've been able to observe it, but that doesn't mean it's unchanging. In fact, the Hubble Space Telescope has been tracking significant changes in the storm over the past decade through the Outer Planet Atmosphere's Legacy Opal program. One of the most notable trends has been the gradual shrinking of the Great Red Spot. This massive anticyclone, which was once large enough to fit 3 Earths side by side, has been steadily decreasing in size. Scientists predict that this shrinking trend will continue, but with an interesting twist. They believe that the Great Red Spot will eventually reach a stable, less elongated shape. As Amy Simon explains, right now it's overfilling its latitude band relative to the wind field. Once it shrinks inside that band, the winds will really be holding it in place. But size isn't the only thing changing about the Great Red Spot. The recent Hubble observations have revealed fascinating details about its color and brightness. When scientists looked at the storm in ultraviolet light, they noticed that the core of the storm becomes brightest when the Great Red Spot is at its largest size during its oscillation cycle. This brightness change indicates less haze absorption in the upper atmosphere, giving us new insights into the storm's vertical structure. The interaction between the Great Red Spot and Jupiter's powerful jet streams is another area of interest. Mike Wong, a co-investigator from the University of California, Berkeley, likens it to a sandwich. As it accelerates and decelerates, the GRS is pushing against the windy jet streams to the north and south of it. It's similar to a sandwich where the slices of bread are forced to bulge out when there's too much filling in the middle. This interplay between the storm and the surrounding atmospheric currents is crucial to understanding why the Great Red Spot has remained at a relatively stable latitude for so long. Unlike on Neptune, where dark spots can drift wildly without strong jet streams to anchor them, Jupiter's Great Red Spot is held in place by these powerful winds, trapped in its southern latitude band. The discoveries about Jupiter's Great Red Spot have implications that extend far beyond this single storm or even Jupiter itself. By studying the largest and longest-lasting storm in our solar system, scientists hope to gain insights into extreme weather patterns on Earth and potentially on exoplanets orbiting distant stars. Understanding the mechanisms that drive and sustain the Great Red Spot could help improve our models of hurricane formation and longevity on Earth. While Earth's storms are much smaller and shorter-lived than Jupiter's, there may be underlying principles that apply to both. The oscillations observed in the Great Red Spot, for instance, might help explain some of the more erratic behaviors seen in terrestrial hurricanes. Moreover, the study of the Great Red Spot provides a unique opportunity to observe long-term atmospheric dynamics in action. Earth's atmosphere is complex and influenced by many factors, making it difficult to study long-term weather patterns. Jupiter, with its massive size and lack of solid surface, serves as a natural laboratory for atmospheric science. The behavior of the Great Red Spot over decades and centuries can offer insights into how weather systems evolve over extended periods. The research also has implications for our understanding of exoplanets. As we discover more planets around other stars, many of which are gas giants like Jupiter, the knowledge gained from studying the Great Red Spot could help us interpret observations of these distant worlds. If we can detect similar storm systems on exoplanets, we might be able to infer details about their atmospheric composition and dynamics based on what we've learned from Jupiter. Furthermore, the unexpected behavior of the Great Red Spot serves as a reminder of the complexity of planetary systems. It shows that even after centuries of observation, there are still surprises to be found in our own solar system. This underscores the importance of continued observation and study of our planetary neighbors. As we push the boundaries of our understanding of planetary weather systems, each new discovery about the Great Red Spot brings us closer to unraveling the mysteries of atmospheric dynamics across the cosmos. It's a testament to the power of persistent observation and the invaluable role of instruments like the Hubble Space Telescope in advancing our knowledge of the universe. While the Hubble Space Telescope has provided unprecedented views of Jupiter's Great Red Spot, the story is far from over. Scientists are eager to continue their observations and gather more data to understand the underlying causes of the storm's newly discovered behaviors. Future high-resolution images from Hubble might reveal other Jovian parameters that could explain the oscillation and other phenomena associated with the Great Red Spot. NASA and other space agencies are also planning future missions that could provide even more detailed information about Jupiter and its iconic storm. The European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, set to launch in the near future, will study Jupiter and its largest moons. While its primary focus will be on the moons, it will also provide valuable data about Jupiter's atmosphere and could offer new perspectives on the Great Red Spot. NASA's Europa Clipper mission, scheduled to launch in the coming years, will primarily study Jupiter's moon Europa but will also have opportunities to observe Jupiter itself. The spacecraft's advanced instruments could provide new insights into the dynamics of Jupiter's atmosphere and the Great Red Spot. Ground-based observatories are also playing a crucial role in studying Jupiter. Advances in adaptive optics and other technologies are allowing Earth-bound telescopes to capture increasingly detailed images of the planet. These observations, combined with data from space-based instruments, will help create a more comprehensive picture of Jupiter's atmospheric dynamics. Citizen scientists and amateur astronomers continue to make valuable contributions to the study of Jupiter and the Great Red Spot. Their consistent observations help fill in gaps between professional studies and can often be the first to spot new developments or changes in the storm's appearance. As our observational capabilities improve, we may be able to peer deeper into the Great Red Spot and better understand its three-dimensional structure. This could help resolve questions about how deep the storm extends into Jupiter's atmosphere and what mechanisms keep it going after all these years. The study of Jupiter's Great Red Spot is an ongoing endeavor that combines the efforts of space agencies, research institutions, and individual enthusiasts around the world. Each new discovery brings us closer to understanding not just this magnificent storm, but the nature of planetary atmospheres throughout the universe. Jupiter's Great Red Spot has not only captured the imagination of scientists but has also made its mark on popular culture. This iconic storm has been featured in numerous science fiction stories, movies, and artworks, serving as a symbol of the mysteries and wonders of our solar system. In literature, the Great Red Spot has been a source of inspiration for many authors. Arthur C. Clarke, in his novel 2010, Odyssey 2, imagined the Great Red Spot as a massive alien life form. Other writers have used it as a setting for interplanetary adventures or as a metaphor for enduring natural forces. The visual arts have also embraced the Great Red Spot. Countless paintings, digital artworks, and sculptures have attempted to capture its swirling beauty. These artistic interpretations often play with scale, juxtaposing the enormous storm with human elements to emphasize its immense size. In cinema and television, the Great Red Spot frequently appears in science fiction productions. It's been portrayed as everything from a portal to other dimensions to a hiding place for alien civilizations. While these depictions are far from scientifically accurate, they speak to the storm's ability to inspire wonder and speculation. Educational programs and planetarium shows often feature the Great Red Spot as a way to introduce audiences to the wonders of our solar system. Its vivid color and massive size make it an ideal subject for engaging viewers of all ages in the marvels of planetary science. The Great Red Spot has even influenced fashion and design, with its distinctive swirling patterns appearing on clothing, accessories, and home decor items. Its unique appearance has made it a recognizable symbol of Jupiter and of space exploration in general. In the realm of music, several composers and musicians have created pieces inspired by the Great Red Spot. These works often attempt to capture the storm's grandeur and mystery through sound, translating visual impressions into auditory experiences. The cultural impact of the Great Red Spot extends to naming conventions as well. Various products, from software applications to beverages, have borrowed its name, capitalizing on its associations with power, endurance, and cosmic wonder. As our scientific understanding of the Great Red Spot evolves, Southwest too does its place in our cultural imagination. Each new discovery about this celestial marvel not only advances our knowledge but also fuels the creative expressions that help make space science accessible and exciting to the general public. The exploration of Jupiter's Great Red Spot reveals that this magnificent storm is much more than just a swirling mass of gas. The recent findings from Hubble have unveiled a dynamic and unpredictable nature that challenges our previous understanding of planetary weather systems. The oscillations and changes in size not only intrigue scientists but also open up new avenues for research that could redefine how we perceive atmospheric phenomena, both on Jupiter and beyond. These revelations remind us that even in our own solar system, there are still mysteries waiting to be uncovered. As observations continue, we may find answers that extend far beyond Jupiter, potentially informing our understanding of weather patterns on Earth and even on distant exoplanets. Thank you for joining us on this fascinating journey through the cosmos. If you enjoyed this video and want to stay updated on the latest discoveries in space science, don't forget to hit that subscribe button and turn on notifications. Your support helps us bring more captivating content to you. Feel free to share your thoughts in the comments below. What surprised you most about the Great Red Spot? Until next time, keep looking up at the stars, because there's always more to discover. In the inky blackness of space, our moon hangs silently, a constant companion to Earth for billions of years. But beneath its dusty, cratered surface lies a secret, one that could change the course of human space exploration forever. For decades, scientists have speculated about the presence of water on the moon, but recent discoveries have blown those theories wide open. Today, we'll be talking about NASA's LRO lunar ice deposits because why not? It's only the most exciting lunar discovery in recent history. Imagine vast reserves of ice hidden in the eternal shadows of lunar craters, just waiting to be tapped. This isn't just a drop in the bucket, we're talking about potential lakes worth of frozen water. What's even more astonishing is that this ice isn't confined to the South Pole. It's spread far and wide across the lunar surface, lurking in places we never thought to look. The implications of this discovery are nothing short of revolutionary. Get ready, space enthusiasts. We're about to embark on a journey that will transform your understanding of our celestial neighbor. Are you prepared for some surprising revelations? Let's dive deep into the subject of lunar ice deposits and uncover the secrets that have been lurking just above us. In the vast expanse of our cosmic neighborhood, the moon has long been a subject of fascination and scientific inquiry. For decades, researchers have speculated about the presence of water ice on our celestial companion. Now, a groundbreaking study using data from NASA's Lunar Reconnaissance Orbiter, LRO, has revealed that lunar ice deposits are far more widespread than previously thought. This discovery has sent ripples of excitement through the scientific community and space exploration agencies worldwide. The moon, once thought to be a dry and desolate world, is now showing us a different face. Hidden in the shadows of its craters and valleys, water ice has been quietly accumulating for billions of years. This isn't just a scientific curiosity, it's a potential game-changer for future lunar missions and our long-term plans for space exploration. Water, after all, is one of the most crucial resources for sustaining human life and enabling long-duration space travel. As we delve into the details of this remarkable finding, we'll explore how this discovery was made, what it means for our understanding of the Moon, and how it could shape the future of space exploration. The Lunar Reconnaissance Orbiter, launched by NASA in 2009, has been tirelessly mapping and studying the Moon's surface for over a decade. Its suite of sophisticated instruments has provided us with unprecedented insights into our nearest celestial neighbor. Among these instruments, the Lunar Exploration Neutron Detector, or LEND, has played a crucial role in uncovering the Moon's icy secrets. Dr. Timothy P. McClanahan of NASA's Goddard Space Flight Center led a team that analyzed data from LEND, focusing on areas known as permanently shadowed regions, or PSRs. These are areas, typically found in deep craters near the lunar poles, that never receive direct sunlight due to the Moon's tilt and topography. The team's findings, published in the Planetary Science Journal, have expanded our understanding of lunar ice distribution. Previous studies had identified ice deposits in large PSRs near the lunar South Pole, including well-known craters like Cabeus, Hayworth, Shoemaker, and Faustini. However, the new analysis reveals that water ice is present in PSRs much farther from the pole than previously thought, extending to at least 77 degrees south latitude. This means that the potential for water ice on the Moon is significantly greater than we had imagined. The study doesn't just confirm the presence of ice, it also provides valuable insights into where we're most likely to find it. Dr. McClanahan and his team found that the highest concentrations of ice are expected in the coldest parts of the PSRs, where temperatures plummet below 75 Kelvin, or about -198 degrees Celsius. These frigid conditions, combined with the perpetual darkness, create perfect preserves for water ice. Interestingly, the research suggests that for every square meter of surface area over these deposits, there could be at least 5 liters of ice within the top meter of the lunar regolith. This estimation, while not definitive, gives us a tantalizing glimpse of the potential water resources waiting to be tapped on the Moon. To understand how scientists detected ice on the Moon, we need to dive into the fascinating world of neutron detection. The LRO's LEND instrument, specifically its collimated sensor for epithermal neutrons, (SEN), played a crucial role in this discovery. But how does measuring neutrons tell us about water ice? The answer lies in the cosmic rays that constantly bombard the Moon's surface. When high-energy galactic cosmic rays, originating from powerful events like exploding stars, hit the Moon, they interact with atoms in the lunar regolith. This interaction creates a shower of particles, including neutrons. These neutrons then bounce around within the top meter or so of the lunar surface, occasionally making their way back into space. It's these escaping neutrons that LEND detects. Here's where it gets interesting. Hydrogen, a key component of water, has a unique effect on these neutrons. Because hydrogen atoms have roughly the same mass as neutrons, they're particularly effective at slowing down neutrons through collisions. This means that in areas where there's a lot of hydrogen, potentially in the form of water ice, we see fewer moderate energy, or epithermal, neutrons escaping. The SEN has a fixed field of view of about 30 kilometers in diameter. By mapping out where it detected fewer epithermal neutrons, the research team could infer the presence of hydrogen-rich areas, likely indicating water ice deposits. But the analysis didn't stop there. The team developed a sophisticated model to account for the varying sizes of PSRs and how they would appear to the instrument. Dr. McClanahan and his colleagues hypothesized that if all PSRs had the same hydrogen concentration, the amount of hydrogen detected should be proportional to the area of the PSR. They tested this hypothesis using data from 502 PSRs, ranging in size from just 4 square kilometers to over 1,000 square kilometers. As expected, they found a stronger correlation between area and hydrogen detection in larger PSRs, while smaller ones showed a weaker relationship. This methodical approach allowed the team to map out not just where ice is likely to be found, but also where it's less likely to accumulate. They discovered that warmer areas that receive periodic sunlight are less likely to harbor significant ice deposits. This makes sense, as exposure to sunlight would cause the ice to sublimate and be lost to space. The study also sheds light on how this ice might have gotten there in the first place. There are several possible sources. Comets and meteors impacting the Moon could have delivered water directly. Alternatively, hydrogen from the solar wind could have combined with oxygen in the lunar regolith to form water molecules. Another possibility is that water vapor could have been released from the moon's interior through volcanic processes. Once formed or delivered, water molecules on the lunar surface lead a precarious existence. They can be dislodged by meteorite impacts, space radiation, or sunlight, causing them to hop across the lunar surface. Many are lost to space, but some lucky molecules find their way into the cold traps of pulsars. Here, in the perpetual darkness and extreme cold, they can remain stable for billions of years, slowly accumulating into the deposits we're now discovering. The discovery of widespread ice deposits on the moon is more than just a scientific curiosity, it has profound implications for the future of space exploration. Water is often called the oil of space due to its crucial importance for sustaining human life and enabling long-duration space missions. The presence of accessible water on the moon could revolutionize our approach to lunar and deep space exploration. First and foremost, water is essential for human survival. Future lunar bases would need a reliable source of water for drinking, hygiene, and growing food in hydroponic systems. Transporting water from Earth is extremely costly, with some estimates suggesting it could cost up to $50,000 per kilogram to ship resources to the moon. Having a local source of water would dramatically reduce the cost and complexity of establishing a permanent human presence on the lunar surface. But the potential of lunar water goes far beyond direct consumption. Water can be broken down into its constituent elements, hydrogen and oxygen, through a process called electrolysis. This has several exciting applications. Oxygen, of course, is crucial for breathing, but it's also a key component of rocket fuel. Hydrogen, when combined with oxygen, creates an extremely efficient propellant. This means that the moon could potentially serve as a cosmic gas station, allowing spacecraft to refuel for journeys to Mars and beyond. The oxygen derived from lunar water could also be used in life support systems and for manufacturing processes on the moon. Meanwhile, hydrogen has potential applications in energy storage and power generation through fuel cells. These capabilities would be crucial for establishing self-sustaining lunar colonies. Moreover, the presence of water ice could support scientific research in various fields. Studying the composition of this ancient ice could provide insights into the early solar system and the origin of water on Earth. The polar regions of the moon, where much of this ice is found, could also serve as ideal locations for astronomical observatories, shielded from Earth's interference and with a stable, cold environment for sensitive instruments. The widespread nature of these ice deposits, as revealed by this study, is particularly exciting for mission planners. It means that future lunar missions have more potential landing sites to choose from, increasing flexibility and safety. Different areas could be selected based on their specific ice concentrations and accessibility, tailored to the goals of each mission. However, accessing and utilizing this ice presents significant challenges. The permanently shadowed regions where the ice is found are extremely cold and dark, making them difficult and dangerous to explore. Future missions will need to develop specialized equipment capable of operating in these harsh conditions. This might include robotic explorers with advanced thermal management systems, or new drilling technologies designed to extract ice from the lunar regolith. There's also the question of how to extract and process the ice efficiently and sustainably. We'll need to develop methods that don't contaminate or deplete this valuable resource. This could involve in-situ resource utilization, ISRU, technologies, which are designed to use local resources for various purposes. As we look to the future, this discovery could accelerate plans for a permanent human return to the moon. NASA's Artemis program, which aims to land the first woman and next man on the moon by 2024, could benefit greatly from this new understanding of lunar ice distribution. International space agencies and private companies are also likely to factor this information into their lunar exploration plans. The discovery of widespread ice deposits on the moon marks a pivotal moment in our understanding of our celestial neighbor and the future of space exploration. It transforms the moon from a seemingly barren world to a potential oasis of resources, waiting to be tapped by future explorers and settlers. This finding is the result of years of meticulous observation and analysis, showcasing the power of long-term scientific missions like the Lunar Reconnaissance Orbiter. It's a testament to human ingenuity and perseverance, using advanced technology to uncover secrets hidden in the shadows of lunar craters for billions of years. As we've explored in this video, the implications of this discovery are far-reaching. It challenges our perceptions of the moon and opens up new possibilities for lunar exploration and utilization. The potential for using lunar water as a resource for sustaining human life, powering spacecraft, and enabling scientific research is truly exciting. However, it's important to remember that this discovery also brings new responsibilities. As we plan future missions to explore and potentially exploit these ice deposits, we must consider the ethical implications. How do we ensure that we use this resource sustainably? How do we balance the needs of human exploration with the preservation of the Moon's unique environment? These are questions that scientists, policymakers, and ethicists will need to grapple with in the coming years. The widespread nature of these ice deposits also highlights the importance of international cooperation in space exploration. No single nation or organization can fully explore and utilize this resource alone. Collaborative efforts will be crucial in developing the technologies needed to access and use lunar ice, as well as in establishing guidelines for its responsible use. As we look to the future, this discovery ignites our imagination about what's possible. Could we see permanent lunar bases within our lifetime, sustained by local water resources? Might the Moon become a stepping stone for human missions to Mars and beyond? Could lunar ice deposits hold clues to the origins of water in our solar system? These questions and possibilities remind us of the enduring value of space exploration. Each new discovery not only advances our scientific knowledge but also pushes the boundaries of what we believe is possible. The Moon, our constant companion in the night sky, continues to surprise and inspire us. As we conclude, it's worth reflecting on how far we've come in our understanding of the Moon. From ancient myths and legends to the first lunar landings, and now to detailed mapping of ice deposits, our journey of lunar exploration is a testament to human curiosity and determination. This latest discovery is not an endpoint, but rather a new beginning, opening up exciting new avenues for exploration and discovery. The widespread ice deposits on the Moon represent more than just a scientific finding, they symbolize hope and possibility. They remind us that even in places we think we know well, there are still secrets waiting to be uncovered. As we continue to explore and learn, who knows what other wonders we might discover, not just on the Moon, but throughout our vast and mysterious universe. As we conclude our exploration of NASA's groundbreaking findings on lunar ice deposits, it's clear that the Moon holds far more than we ever imagined. The discovery of widespread ice, not just concentrated at the poles but across various regions, opens up a world of possibilities for future lunar missions. This resource could be vital for sustaining human life, fueling spacecraft, and even conducting scientific research that deepens our understanding of the solar system. The implications are profound. With the potential for in-situ resource utilization, we could establish a permanent human presence on the Moon, paving the way for further exploration of Mars and beyond. Each new piece of information about lunar ice brings us closer to realizing these ambitious goals and transforming our vision of space travel. Thank you for joining us on this fascinating journey into the secrets of our Moon. If you found this video enlightening, please give it a thumbs up and share it with fellow space enthusiasts. We'd love to hear your thoughts. What do you think about the potential for lunar ice? Are you excited about future missions? Don't forget to subscribe to our channel for more engaging content on space exploration and scientific discoveries. Hit that notification bell so you never miss an update. Together, let's continue to explore the wonders of our universe. In the vast expanse of our solar system, a groundbreaking collaboration is unfolding that could change our understanding of distant worlds. NASA's Hubble Space Telescope and the New Horizons spacecraft have joined forces to take a simultaneous look at one of the most enigmatic planets in our cosmic neighborhood, Uranus. Today, we'll be talking about this extraordinary study because why not? Picture two iconic space explorers, Hubble, orbiting Earth and capturing breathtaking details, and New Horizons, having journeyed far beyond Pluto, offering a unique perspective from billions of miles away. Together, they are unraveling secrets about Uranus that could redefine how we understand not just our own solar system but also the myriad exoplanets scattered throughout the galaxy. What mysteries lie hidden in Uranus's swirling clouds? How might these observations impact our search for life beyond Earth? The answers could reshape our expectations for future missions aimed at exploring distant worlds. Let's dive deep into the fascinating subject of NASA's Hubble and New Horizons teaming up for a simultaneous look at Uranus. In a groundbreaking collaboration, NASA's Hubble Space Telescope and New Horizons spacecraft have joined forces to study Uranus from two vastly different perspectives. This unique dual observation provides scientists with invaluable data that could revolutionize our understanding of exoplanets, worlds beyond our solar system. Uranus, the seventh planet from the Sun, serves as an ideal proxy for many known exoplanets. As a gas giant, it shares similarities with numerous planets discovered orbiting distant stars. By comparing high-resolution images from Hubble with the more distant view captured by New Horizons, astronomers aim to refine their techniques for future exoplanet observations. This collaborative effort between two of NASA's most iconic space explorers offers a rare opportunity to study Uranus from multiple angles simultaneously. The data gathered will not only enhance our knowledge of this mysterious ice giant but also pave the way for more accurate interpretations of exoplanet observations in the future. As we delve into the details of this extraordinary study, we'll explore how these observations were made, what they reveal about Uranus, and how they might shape our approach to studying distant worlds in the years to come. The power of this study lies in its unique dual perspective. On one side, we have the Hubble Space Telescope, orbiting Earth at a distance of about 340 miles. From this vantage point, Hubble was approximately 1.7 billion miles away from Uranus during the observations. Despite this vast distance, Hubble's advanced optics allowed it to capture high-resolution images of the planet's dayside, revealing intricate details of its atmospheric features, including clouds and storms. On the other side of this cosmic equation is New Horizons, a spacecraft that has ventured far beyond the reaches of our planetary neighborhood. At the time of the observations, New Horizons was positioned on the far side of Uranus, a staggering 6.5 billion miles away from the ice giant. This unique positioning allowed scientists to study Uranus's twilight crescent, a perspective impossible to achieve from Earth or near-Earth orbit. The contrast between these two views is stark. While Hubble provided detailed, close-up images of Uranus's atmospheric dynamics, New Horizons saw the planet as little more than a few pixels in its multispectral visible imaging camera. This disparity in resolution mirrors the challenges astronomers face when attempting to image distant exoplanets. Lead author Samantha Hassler of the Massachusetts Institute of Technology explains, Uranus appears as just a small dot on the New Horizons observations, similar to the dots seen of directly imaged exoplanets from observatories like Webb or ground-based observatories. Hubble provides context for what the atmosphere is doing when it was observed with New Horizons. This combination of detailed and distant observations allows scientists to bridge the gap between our understanding of nearby planets and the faint signals we receive from exoplanets light-years away. By studying how Uranus appears from these different perspectives, researchers can better interpret the limited data available from exoplanet observations, potentially unlocking new insights into these distant worlds. As with many scientific endeavors, this study of Uranus yielded some unexpected results. Hassler and her team found that Uranus appeared dimmer than predicted in the New Horizons data. This discovery highlights the complexities involved in interpreting planetary observations, especially when dealing with different viewing angles and distances. The dimmer appearance of Uranus from New Horizons' perspective could have significant implications for how we understand and interpret exoplanet observations. Many exoplanets are only visible to us when they're partially illuminated by their host stars, similar to the crescent phase of Uranus observed by New Horizons. This finding suggests that exoplanets might be dimmer than we expect at these partial and high-phase angles, which could affect our estimates of their size, composition, and atmospheric properties. Another intriguing discovery came from comparing the observations over time. Both Hubble and New Horizons noted that Uranus's brightness remained consistent as the planet rotated. This stability suggests that the cloud features on Uranus were not changing significantly during the observation period. Such information is crucial for understanding the dynamic nature of planetary atmospheres, both in our solar system and beyond. The study also revealed that Uranus's atmosphere reflects light differently when observed at partial phase. This finding could be particularly valuable for future exoplanet studies, as it provides a reference point for interpreting the light reflected by distant planets under similar conditions. These unexpected results underscore the importance of multi-perspective observations in planetary science. By combining data from different vantage points, scientists can uncover nuances that might be missed from a single observational platform. This approach not only enhances our understanding of planets within our solar system but also improves our ability to interpret data from distant exoplanets. As we continue to explore the cosmos and search for potentially habitable worlds, studies like this one remind us of the complexities involved in planetary observation and the need for innovative approaches to overcome these challenges. The insights gained from this dual observation of Uranus have far-reaching implications for the field of exoplanet research. As we look to the stars in search of other worlds, the lessons learned from studying our own solar system become invaluable tools in interpreting the faint signals from distant planets. One of the key challenges in exoplanet research is the difficulty of directly imaging these distant worlds. Unlike the planets in our solar system, exoplanets appear as mere pinpoints of light, even through our most powerful telescopes. The comparison between Hubble's detailed view of Uranus and New Horizons' distant perspective provides a crucial link between these two extremes. By understanding how a known planet like Uranus appears from different distances and angles, scientists can better interpret the limited data available from exoplanet observations. This ground truth data from Uranus serves as a benchmark, helping researchers develop more accurate models for understanding the atmospheric conditions, cloud patterns, and other characteristics of distant exoplanets. The study's findings about Uranus's dimmer-than-expected appearance and consistent brightness during rotation are particularly significant. These observations suggest that our current models for predicting exoplanet brightness and variability may need refinement. Such adjustments could lead to more accurate estimates of exoplanet sizes, compositions, and potential habitability. Moreover, this research highlights the importance of observing planets at different phases. The unique perspective offered by New Horizons, capturing Uranus's twilight crescent, mimics the partial illumination we often see in exoplanet observations. Understanding how planetary atmospheres reflect light under these conditions is crucial for interpreting exoplanet data accurately. As we prepare for the next generation of space telescopes and exoplanet missions, studies like this one play a vital role in shaping our observational strategies. By learning from the familiar planets in our cosmic backyard, we enhance our ability to explore and understand the vast array of worlds that exist beyond our solar system. The collaborative study of Uranus by Hubble and New Horizons sets the stage for future missions dedicated to exoplanet research. NASA has several ambitious projects in the pipeline that will build upon these findings and push the boundaries of our understanding of distant worlds. One such mission is the Nancy Grace Roman Space Telescope, scheduled for launch by 2027. This advanced observatory will employ a coronagraph, a sophisticated instrument designed to block out the bright light of stars. This technology will allow astronomers to directly observe gas-giant exoplanets orbiting other stars, potentially revealing details about their atmospheres and compositions. Even more ambitious is NASA's Habitable Worlds Observatory, currently in its early planning stages. This groundbreaking telescope will be the first of its kind, specifically designed to search for atmospheric biosignatures on Earth-sized, rocky planets orbiting other stars. The insights gained from the Uranus study will be crucial in interpreting the data from these future missions, helping scientists distinguish between different types of exoplanets and identify potential candidates for habitability. Alan Stern, the principal investigator of the New Horizons mission, emphasizes the significance of these observations. These landmark New Horizons studies of Uranus from a vantage point unobservable by any other means add to the mission's treasure trove of new scientific knowledge, and have yielded surprising new insights into the worlds of our solar system. As we look to the future, the expectations for exoplanet research are higher than ever. The combined power of these upcoming missions, informed by studies like the Uranus observations, promises to revolutionize our understanding of planetary systems throughout the galaxy. We may soon be able to characterize the atmospheres of distant worlds with unprecedented detail, potentially uncovering evidence of life beyond Earth. The journey from observing the ice giants in our own solar system to exploring Earth-like planets light years away is a testament to human curiosity and technological advancement. As we continue to push the boundaries of space exploration, each discovery brings us closer to answering some of the most profound questions about our place in the universe. As we've explored today, the collaboration between NASA's Hubble Space Telescope and New Horizons has opened new doors in our understanding of Uranus and, by extension, the study of exoplanets. The insights gained from observing this distant gas giant not only enhance our knowledge of our own solar system but also provide a crucial framework for interpreting the faint signals we receive from worlds beyond our reach. The unexpected findings regarding Uranus's brightness and atmospheric behavior remind us that there is still so much to learn about these distant planets. Each observation brings us closer to unraveling the mysteries of the cosmos, helping scientists refine their techniques and expectations for future missions. As we prepare for advanced telescopes like the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory, the groundwork laid by studies like this one will be invaluable. Thank you for joining us on this journey through space exploration. If you found this video enlightening, please give it a thumbs up and share it with fellow space enthusiasts. Don't forget to subscribe for more captivating content about our universe and the ongoing discoveries that shape our understanding of it. Your support helps us continue to bring you the latest in space science and exploration. Stay curious, and we'll see you in the next video as we continue to explore the wonders of our universe together. It's 2030, and the International Space Station, our home away from home for over 2 decades, is making its final descent. As it streaks across the sky in a blaze of glory, you might think humanity's presence in low Earth orbit is coming to an end. But hold on tight, because the story is just beginning. Enter Vast Space, a company with a vision so ambitious it makes sci-fi writers look conservative. They're not just planning to replace the ISS, they're aiming to revolutionize our entire approach to living and working in space. Today, we'll be talking about Haven 2, the next-generation space station that could redefine our future among the stars, because why not dream big when it comes to space? But here's where things get really interesting. Haven 2 isn't just another tin can floating in space. It's a modular marvel, designed to grow and adapt over time. And get this, it's got features that would make even the most seasoned astronaut's jaw drop. We're talking about a window so large you could practically parkour in zero gravity while gazing at Earth. So, prepare for launch as we dive deep into the world of Haven 2. The question isn't just whether this private space station can fill the ISS's shoes, it's whether it can take humanity's space ambitions to new heights. As we gaze up at the night sky, a bright speck moves across the stars, the International Space Station, humanity's home in orbit for over 2 decades. But this beacon of scientific progress is nearing its final days. In 2030, the ISS will make its fiery descent back to Earth, marking the end of an incredible chapter in space exploration. With the clock ticking, the race is on to create the next generation of orbital outposts. Private companies are stepping up to the challenge, vying to build the world's first commercial space stations. Among these ambitious contenders is Vast Space, a US-based company with a bold vision for the future of human habitation beyond our planet. At the 75th International Astronautical Congress in Milan, Italy, Vast Space unveiled their answer to the looming void left by the ISS's retirement. Enter Haven 2, a cutting-edge private space station designed to carry the torch of orbital research and exploration into a new era. This ambitious project represents not just a replacement for the ISS, but a significant leap forward in our capabilities to live and work in space. As we stand on the brink of this new frontier in space exploration, questions abound. How will Haven 2 compare to the ISS? What new possibilities will it unlock for scientific research and commercial ventures in orbit? And perhaps most intriguingly, what does this shift towards private space stations mean for the future of international cooperation in space? Haven 2 isn't just another space station, it's the embodiment of Vast Space's ambitious vision to pioneer long-term living and thriving in space. Max Haut, the CEO of Vast Space, has set his sights on winning NASA's coveted commercial LEO destination contract, positioning Haven 2 as the true successor to the International Space Station. But Rome wasn't built in a day, and neither will Haven 2. The journey begins with Haven 1, a precursor station set to launch in 2025. This initial outpost will serve as a proving ground for Vast Space's technologies and operations, paving the way for the more expansive Haven 2. What sets Haven 2 apart is its modular design, inspired by the ISS itself. This approach allows for gradual construction in low Earth orbit, with each new module expanding the station's capabilities. The first 16-foot-long unit is slated to become fully operational by 2028, ensuring a seamless transition as the ISS approaches retirement. But Vast Space isn't stopping there. Between 2030 and 2032, 3 additional modules will join the initial unit, each one not only increasing the station's volume but also enhancing its life support systems and research capabilities. This incremental growth strategy allows Haven 2 to adapt and evolve, meeting the changing needs of scientific research and space exploration. As we look to the future of human presence in low Earth orbit, Haven 2 stands as a testament to human ingenuity and the power of commercial space ventures. But what exactly will this next-generation space station offer to scientists, astronauts, and perhaps even space tourists? At the heart of Haven 2's mission is its commitment to advancing scientific research in the unique environment of microgravity. The station's lab module is set to become a state-of-the-art facility, supporting a wide range of experiments that could unlock new discoveries in fields like medicine, materials science, and biotechnology. Vast Space has designed Haven 2 to meet and exceed NASA's basic laboratory capabilities criteria, ensuring that it can seamlessly continue the groundbreaking work currently being conducted on the ISS. From studying the effects of long-term space exposure on the human body to developing new pharmaceuticals and materials, Haven 2 will be at the forefront of orbital research. But Haven 2 isn't just about replicating the ISS's capabilities, it's about pushing the boundaries of what's possible in space. The station will feature advanced in-space manufacturing facilities, opening up new possibilities for producing goods and materials that can only be created in the unique conditions of microgravity. One of the most exciting features of Haven 2 is its massive 41-foot-wide cupola window. This unparalleled viewing port will not only provide breathtaking views of Earth and space but also serve as a platform for Earth observation studies and space photography. Imagine the incredible images and data that could be captured from this vantage point, furthering our understanding of our planet and the cosmos. As we explore the potential of Haven 2, it's clear that this isn't just a replacement for the ISS, it's a leap forward in our capabilities to live, work, and conduct research in space. But how will this commercial venture impact international cooperation in space exploration? While Haven 2 represents a shift towards commercialization in space, it's being designed with international collaboration firmly in mind. The success of the International Space Station has proven the immense value of global cooperation in space exploration, and Vast Space is keen to continue this legacy. Andrew Feustel, a 23-year NASA veteran astronaut and advisor to Vast Space, emphasizes that Haven 2 is being developed with compatibility as a key feature. This means that international partners will be able to integrate seamlessly into this next-generation platform, fostering a new era of global cooperation in space. The vision for Haven 2 extends beyond just scientific research. It's about creating opportunities for technological advancements that can benefit both new and current sovereign partners, as well as industries around the world. This approach could democratize access to space, allowing more countries and organizations to participate in orbital research and exploration. Imagine a future where scientists from dozens of nations work side by side in Haven 2's labs, or where space agencies from around the globe coordinate missions using the station as a staging point. This level of international collaboration could accelerate our progress in space exploration and drive innovations that improve life on Earth. As we look to the stars, Haven 2 stands as a symbol of what we can achieve when we combine commercial innovation with global cooperation. But what specific features will set this station apart from its predecessors and competitors? Haven 2 is not just a space station, it's a marvel of engineering designed to surpass all other proposed orbital facilities in terms of volume, functionality, and operational efficiency. Let's explore some of the cutting-edge features that will make Haven 2 the benchmark for next-generation space stations. One of the most striking aspects of Haven 2 is its array of windows. In addition to the massive cupola, each module will feature its own 3.6-foot-wide viewing ports, bringing the total number to 16. These windows will not only provide stunning views but also serve critical functions for Earth observation and space monitoring. On the exterior, Haven 2 will boast impressive payload hosting capabilities. A robotic arm, similar to the Canadarm on the ISS, will assist with maintenance and the capture of visiting vehicles. The station will also feature both an external payload airlock and an extravehicular activity airlock, enabling spacewalks and the deployment of experiments outside the station. Inside, Haven 2's modular design allows for flexible configuration of research areas and living spaces. Advanced life support systems will create a comfortable and sustainable environment for long-duration stays, while state-of-the-art communication systems will keep the station connected with Earth. As we consider these impressive features, it's clear that Haven 2 is poised to redefine our capabilities in low Earth orbit. But with several companies vying for the chance to build the next great space station, what gives Vast Space the edge in this? As the 2030 deadline for the ISS retirement looms, the race to establish the next generation of space stations is heating up. Vast Space isn't alone in this endeavor. Companies like Blue Origin, Axiom Space, and Northrop Grumman are all developing their own concepts for commercial space stations. So what gives Haven 2 an edge in this cosmic competition? For starters, Vast Space's approach of launching Haven 1 as a precursor mission provides them with valuable real-world experience in operating a space station. This stepping stone approach allows them to refine their technologies and procedures before scaling up to Haven 2. Another advantage lies in Haven 2's modular design. By launching and assembling the station in stages, Vast Space can adapt to changing requirements and incorporate new technologies as they become available. This flexibility could prove crucial in the rapidly evolving landscape of commercial space exploration. Vast Space is also leveraging partnerships with established players in the space industry. Their collaboration with SpaceX for launches demonstrates their ability to work with proven technology while focusing on their core expertise in space habitation. As the competition intensifies, the ultimate winner may be determined not just by technical capabilities, but by factors such as cost-effectiveness, adaptability, and appeal to both government and private sector clients. With its innovative design and forward-thinking approach, Haven 2 is certainly a strong contender in the race to become the next home for humanity in orbit. Haven 2 represents a bold leap into the future of space exploration, offering a glimpse of what's possible when innovation meets ambition. As we've explored today, this next-generation space station isn't just about replacing the ISS, it's about redefining our relationship with space itself. With its modular design and advanced capabilities, Haven 2 stands to become a cornerstone for scientific research, international collaboration, and even commercial ventures in low Earth orbit. The potential for groundbreaking discoveries in microgravity is immense, and Haven 2 is poised to facilitate research that could lead to advancements in medicine, materials science, and technology. Furthermore, its design encourages global partnerships, fostering cooperation among nations and organizations that could change the landscape of space exploration for years to come. As we look ahead to the launch of Haven 1 in 2025 and the subsequent deployment of Haven 2, one thing is clear: the future of human presence in space is bright. The journey is just beginning, and we are all part of this incredible adventure. Thank you for joining us on this exploration of Haven 2 and its promise for humanity's future in space. If you enjoyed this video and want to stay updated on all things related to space exploration and technology, make sure to subscribe to our channel. Your support helps us continue bringing you exciting content. Until next time, keep looking up at the stars. In the depths of space, a cosmic giant is wreaking havoc on an unprecedented scale. This isn't your average celestial body. We're talking about one of the oldest and most powerful entities ever discovered in our universe. An ancient supermassive black hole, lurking in the cosmos when the universe was barely 700 million years old, is blasting its surroundings with winds so fierce they're literally tearing its home galaxy apart. This cosmic behemoth, known to astronomers as J1007-2115, is pushing the boundaries of our understanding of the early universe. Its very existence challenges our theories about how quickly these cosmic monsters can form and grow. But it's not just its age that's turning heads in the scientific community. It's the sheer destructive power it wields. Imagine winds so powerful they can stretch across 7,500 light-years, moving at speeds that would make your head spin. We're talking about 4.7 million miles per hour. These aren't gentle breezes, they're galaxy-killing gusts that are forcefully evicting the building blocks of stars from their cosmic neighborhood. The James Webb Space Telescope, our latest and greatest eye on the cosmos, has captured this celestial drama in unprecedented detail. It's giving us a front-row seat to one of the most violent and influential processes in the universe, one that could hold the key to understanding how galaxies live and die. Today, we'll be talking about these galaxy-killing winds from ancient supermassive black holes because why not? It's only the key to unraveling the mysteries of cosmic evolution and potentially the fate of our own Milky Way. Let's dive deep into this subject and explore the turbulent world of quasar winds and their galaxy-shaping power. We'll uncover how these cosmic tempests are changing our understanding of the universe and what they might mean for the future of galaxies across the cosmos. The James Webb Space Telescope has unveiled a cosmic spectacle that's rewriting our understanding of the early universe. Peering back through time, this remarkable instrument has captured the image of a supermassive black hole, designated J1007-2115, that existed when the universe was a mere infant, just 700 million years old. This ancient behemoth isn't just sitting quietly in space, it's unleashing a tempest of galactic proportions. Imagine winds so powerful they could span 7,500 light-years, that's like lining up 3,750 solar systems end to end. These aren't gentle breezes we're talking about. These winds are hurtling through space at a mind-bending 4.7 million miles per hour, over 6,000 times faster than the speed of sound. With each passing year, these cosmic gales expel enough material to create 300 suns. But what does this mean for the galaxy hosting this tempestuous black hole? It's like watching a celestial drama unfold in slow motion. These winds are literally blowing away the building blocks of stars, the gas and dust that would otherwise coalesce to form new celestial bodies. It's a process that could effectively sterilize the entire galaxy, halting star formation in its tracks. This discovery isn't just breaking records for being one of the earliest and most distant quasars ever observed. It's providing us with a front-row seat to cosmic processes that shape the very fabric of our universe. As we watch this ancient quasar blow its mighty winds, we're witnessing the potential birth of what astronomers call a dead galaxy, one where the frenzy of star formation has been brought to a standstill. The implications of this discovery stretch far beyond this single galaxy. It's forcing astronomers to reconsider how quickly supermassive black holes can grow and begin influencing their surroundings. The presence of such a massive and active black hole so early in the universe's history is challenging our models of cosmic evolution. At the heart of this cosmic spectacle lies a phenomenon that has captivated astronomers for decades: quasars. These cosmic lighthouses are among the brightest objects in the universe, outshining entire galaxies with their intense radiance. But what powers these cosmic beacons? The answer lies in the monstrous black holes at their cores. Imagine a black hole so massive that it dwarfs our Sun millions or even billions of times over. These are the engines of quasars, cosmic giants that warp the very fabric of space and time around them. But a black hole alone does not a quasar make. The secret ingredient is food, vast amounts of gas and dust swirling around the black hole in what astronomers call an accretion disk. As this cosmic buffet spirals ever closer to the black hole's maw, friction heats it to incredible temperatures. This superheated material glows with an intensity that can outshine the combined light of every star in its host galaxy. It's this process that gives quasars their characteristic brilliance, making them visible across billions of light years. But not all supermassive black holes are created equal. Take, for instance, the black hole at the center of our own Milky Way, Sagittarius A star. Despite its impressive mass of about 4 million suns, it's a quiet neighbor, lacking the abundant fuel needed to shine as a quasar. It's a stark contrast to the voracious appetite of J1007-2115, which is gorging itself on surrounding matter at a prodigious rate. The intense radiation produced by an active quasar does more than just create a cosmic light show. It also generates powerful winds that can shape the destiny of entire galaxies. These winds, composed of superheated gas and charged particles, stream outward from the quasar at incredible speeds. They act like cosmic sculptors, carving out vast bubbles in the intergalactic medium and influencing the evolution of their host galaxies. Understanding quasars and the supermassive black holes that power them is crucial to unraveling the mysteries of galaxy formation and evolution. These cosmic titans play a pivotal role in the life cycles of galaxies, potentially determining whether a galaxy will become a stellar nursery or a cosmic graveyard. As we peer deeper into the universe with instruments like the James Webb Space Telescope, we're uncovering the profound influence these objects have had on shaping the cosmos we see today. The discovery of J1007-2115's powerful winds has opened a window into the complex and often violent relationship between supermassive black holes and their host galaxies. These winds, racing outward at speeds 6,000 times faster than sound, are more than just an impressive cosmic phenomenon, they're agents of profound galactic change. Imagine a galactic-scale leaf blower, capable of sweeping away the very building blocks of stars. That's essentially what these quasar winds do. By expelling vast quantities of gas and dust from the galaxy, they can effectively shut down the galaxy's star-forming factories. This process, known as quenching, can transform a vibrant, star-forming galaxy into a cosmic ghost town, where the birth of new stars grinds to a halt. In the case of J1007-2115, we're witnessing this process in its early stages. The James Webb Space Telescope has revealed a galaxy still rich in the dense molecular gas and dust needed for star formation. Currently, this cosmic nursery is churning out new stars at a rate of 80 to 250 solar masses each year, a veritable stellar baby boom. But the clock is ticking. The relentless assault of the quasar winds threatens to bring this stellar production line to a screeching halt. But the story doesn't end there. These winds don't just affect the galaxy's ability to form new stars, they also regulate the growth of the supermassive black hole itself. It's a cosmic case of biting the hand that feeds you. By blowing away the very material that fuels its growth, the black hole creates a self-limiting mechanism. This feedback loop may explain why we don't see even more massive black holes in the universe. They effectively cut off their own food supply. This self-regulation has profound implications for our understanding of galaxy evolution. It suggests a delicate balance between the growth of supermassive black holes and the development of their host galaxies. Too much black hole activity, and the galaxy risks having its star-forming potential snuffed out prematurely. Too little, and the galaxy might not benefit from the mixing and redistribution of elements that these winds can provide. The discovery of such powerful winds in a galaxy so early in the universe's history is forcing astronomers to rethink the timeline of galactic evolution. It suggests that the processes shaping galaxies were already in full swing when the universe was just 5% of its current age. This raises intriguing questions about how quickly supermassive black holes can form and grow in the cosmic dawn. As we continue to study J1007-2115 and other similar objects, we're piecing together the cosmic puzzle of how galaxies are born, live, and eventually die. Each new observation brings us closer to understanding our own galactic home and its possible fate in the distant future. The discovery of J1007-2115 and its powerful winds is more than just another entry in the astronomical record books. It's a cosmic time capsule, offering us a glimpse into the universe's tumultuous youth. By observing such ancient and distant objects, we're not just satisfying scientific curiosity, we're piecing together the epic saga of cosmic evolution. Imagine peering through a telescope and seeing not just distant space, but distant time. That's exactly what we're doing when we observe J1007-2115. We're seeing this quasar as it was 13.1 billion years ago, when the universe was a mere 700 million years old. To put that in perspective, if the universe's history were compressed into a single Earth year, we'd be watching events unfold on January 14th. The Earth wouldn't form until September, and humans wouldn't arrive until the last hour of December 31st. This early appearance of such a massive and active black hole is forcing astronomers to rethink their models of how these cosmic giants form and grow. It's as if we found a fully grown adult in a nursery. It simply shouldn't be there according to our previous understanding. This discovery suggests that the seeds of supermassive black holes must have been planted very early in the universe's history, and they must have grown at an astounding rate. But J1007-2115 isn't just challenging our ideas about black hole formation. It's also providing crucial insights into the evolution of galaxies. The powerful winds we're observing show that the processes shaping galaxies were already in full swing less than a billion years after the Big Bang. This means that the cosmic forces molding the universe we see today were already hard at work when the cosmos was in its infancy. These observations are also shedding light on the complex interplay between supermassive black holes and their host galaxies. The fact that such powerful winds exist so early in cosmic history suggests that the relationship between black holes and galaxies was established very quickly. This coevolution of black holes and galaxies is a key piece of the puzzle in understanding how the universe transitioned from the cosmic dark ages to the star-filled cosmos we see today. As we continue to push the boundaries of our observations, probing ever deeper into cosmic history with instruments like the James Webb Space Telescope, we're likely to uncover more objects like J1007-2115. Each discovery will add another piece to the cosmic puzzle, helping us to build a more complete picture of how our universe came to be. These early universe observations are not just about understanding the past, they're crucial for predicting the future. By understanding how galaxies and black holes evolved in the early universe, we can better model how they will continue to change over cosmic time. This knowledge could ultimately help us understand the fate of our own Milky Way galaxy and the supermassive black hole lurking at its center. As we've explored, the discovery of the ancient quasar J1007-2115 and its powerful galaxy-killing winds offers profound insights into the early universe. These winds, capable of expelling vast amounts of gas and dust, have the potential to halt star formation and reshape entire galaxies. This remarkable phenomenon not only challenges our understanding of how quickly supermassive black holes can grow but also highlights the intricate relationship between these cosmic giants and their host galaxies. The implications of this research extend far beyond J1007-2115. By studying such ancient objects, astronomers are piecing together the history of our universe and gaining a clearer picture of how galaxies evolve over billions of years. The James Webb Space Telescope is providing us with unprecedented views into this cosmic drama, allowing us to witness the forces that have shaped the universe since its infancy. Thank you for joining in on this exploration of quasar winds and their impact on galaxy evolution. If you enjoyed this video and want to stay updated on more fascinating discoveries from the universe, don't forget to subscribe and hit that notification bell. Your support helps us bring you more content that delves into the wonders of space and science. Feel free to share your thoughts in the comments below. What do you find most intriguing about supermassive black holes and quasars? We love hearing from you. Until next time, keep looking up at the stars and wondering about the mysteries they hold. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. In the vast depths of space and time, a cosmic mystery has been unfolding for billions of years. But only now, with the incredible power of the James Webb Space Telescope, are we beginning to unravel its secrets. A galaxy, formed when the universe was just a fledgling entity, has been growing at an astonishing rate, far quicker than anyone could have anticipated. It's as if we are witnessing the evolution of a city, rapidly constructed and expanding overnight, yet the scale is far grander, reaching beyond the confines of our imagination. This galaxy's rapid development defies the conventional understanding of cosmic growth, revealing new insights into the forces shaping the universe. It's a glimpse into a time when the universe was still in its infancy, yet already brimming with complex and awe-inspiring phenomena. Today, we'll be talking about inside-out galaxy growth in the early universe, because why not? It's a tale of stellar birth, dark matter, and the very fabric of spacetime itself. This isn't just any galaxy we're looking at. It's a window into our own cosmic past, a glimpse of how our Milky Way might have looked in its infancy. This galaxy is defying all expectations. Its rapid and unusual growth is pushing scientists to re-evaluate everything they thought they knew about galaxy formation. What does this mean for our understanding of the universe, and what other secrets might be lurking in the cosmic dawn? Let's dive deep into this subject of early galaxy formation and uncover the mysteries that have been waiting 13 billion years to be revealed. The James Webb Space Telescope has revolutionized our ability to peer into the distant past of our universe. In a groundbreaking observation, astronomers have witnessed the inside-out growth of a galaxy that existed a mere 700 million years after the Big Bang. This discovery is reshaping our understanding of how galaxies form and evolve in the early universe. The galaxy in question is a cosmic infant compared to our Milky Way, measuring only 1/100th of its size. Yet, despite its small stature, this ancient galaxy displays a surprisingly mature structure. At its heart lies a dense core of stars, surrounded by less crowded outer regions where new stars are forming at a rapid pace. This structure, reminiscent of a bustling city with a dense downtown and sprawling suburbs, offers a unique glimpse into the processes that shape galaxies in their infancy. Before the advent of the James Webb Space Telescope, such detailed observations of early galaxies were beyond our reach. The telescope's unprecedented sensitivity and resolution have opened a window to a period of cosmic history that was previously shrouded in mystery. This discovery marks the earliest ever detection of inside-out galactic growth, a phenomenon that astronomers have long theorized but never before witnessed in such an early stage of the universe. The implications of this discovery are far-reaching. By studying galaxies like this one, scientists hope to unravel the complex processes that transform primordial gas clouds into the intricate structures we see in the present-day universe. This observation provides a crucial data point in our understanding of cosmic evolution, bridging the gap between theoretical models and observable reality. The discovery of this ancient galaxy's inside-out growth pattern has sparked intense interest among astronomers. Dr. Sandro Tacc from Cambridge's Cavendish Laboratory, who co-led the study, explains the significance. The question of how galaxies evolve over cosmic time is a fundamental one in astrophysics. With Webb, we're now able to probe the first billion years of cosmic history, opening up entirely new avenues of research. To understand how galaxies grow, astronomers often use the analogy of a spinning figure skater. As a galaxy accretes gas from its surroundings, it's similar to a skater pulling in their arms. This action causes the skater, or in this case, the galaxy, to spin faster and faster. The result is often the formation of spiral or disk shapes that we commonly observe in mature galaxies. In the case of this early galaxy, the process seems to be in its initial stages. The dense core suggests that the galaxy has already undergone significant star formation in its center. However, the real action is happening in the outskirts, where star formation is accelerating. This pattern of growth, with a well-established core surrounded by regions of increasing star formation activity as you move outwards, is a hallmark of inside-out growth. What makes this observation particularly intriguing is the galaxy's age. At just 700 million years old, it's a cosmic toddler compared to our 13.8 billion-year-old universe. Yet it already shows signs of mature structure and rapid growth. This suggests that the conditions in the early universe may have been particularly conducive to rapid galaxy formation and evolution. The galaxy's growth rate is truly astounding. While our Milky Way takes about 10 billion years to double its mass, this young galaxy is doubling its stellar mass in the outskirts roughly every 10 million years. This rapid growth provides a unique opportunity to study how galaxies transform from clouds of gas into the complex structures we observe today. The James Webb Space Telescope's advanced instruments have made this discovery possible by allowing astronomers to measure light across various wavelengths. This capability enables researchers to estimate the number of young and old stars in the galaxy, providing a deeper understanding of its stellar mass and growth patterns. William Baker, a PhD student at the Cavendish Laboratory and co-author of the study, emphasizes the transformative nature of Webb. One of the many reasons that Webb is so revolutionary for astronomers is that we're now able to observe what had previously been predicted through modeling. It's like being able to check your homework. The researchers used a technique called forward modeling to account for instrumental effects and extract detailed information about the galaxy's structure. This involved creating simulated observations based on theoretical models and then comparing them to the actual data from Webb. By iteratively refining their models, the team was able to reconstruct the galaxy's properties with unprecedented accuracy. Their analysis revealed a complex picture of the galaxy's structure. The core contains older stars, suggesting it formed earlier in the galaxy's history. Meanwhile, the surrounding disk component is undergoing very active star formation, with new stars being born at a furious pace. Even more intriguingly, the researchers detected a star-forming clump even further out from the galaxy's center, possibly indicating the beginnings of spiral arm formation. The Webb telescope's ability to capture light from the infrared part of the spectrum is crucial for studying these early galaxies. As the universe expands, light from distant objects is stretched, shifting visible light into the infrared range. Webb's infrared capabilities allow it to detect this ancient light, providing a clear view of galaxies that would be invisible to optical telescopes. Moreover, Webb's large mirror and advanced detectors allow it to collect extremely faint signals from these distant galaxies. This sensitivity is what enables astronomers to study the detailed structure and composition of galaxies that existed when the universe was less than 5% of its current age. The discovery of this rapidly growing galaxy in the early universe has shed new light on the physical processes driving galaxy formation. In the cosmic infancy, the universe was a very different place. It was denser, hotter, and filled with primordial gas, mostly hydrogen and helium. The question that has long puzzled astronomers is how this uniform soup of elements coalesced into the structured galaxies we see today. The observed galaxy provides some crucial clues. Its dense core suggests that gravity played a key role early on, pulling matter together into a compact region. This gravitational collapse would have triggered the first burst of star formation, creating the older stellar population we see in the galaxy's center. But the story doesn't end there. The accelerated star formation in the galaxy's outskirts points to a more complex process at work. As the initial stars formed and died, they would have released heavier elements into the surrounding gas. This enriched material, combined with the ongoing infall of pristine gas from the cosmic web, created ideal conditions for a second wave of star formation. The rapid growth rate observed in this galaxy also hints at the efficiency of early star formation. In the present-day universe, various factors like supernovae and active galactic nuclei can disrupt star formation. But in the early universe, these feedback mechanisms may have been less prevalent, allowing for more unimpeded star formation. Another fascinating aspect is the role of dark matter. While invisible, dark matter is thought to provide the gravitational scaffolding upon which galaxies form. The compact nature of this early galaxy suggests that dark matter halos in the early universe may have been denser or more concentrated than previously thought. While the discovery of this rapidly growing early galaxy is groundbreaking, it's essential to place it in context. Astronomers are now analyzing data from other galaxies observed by Webb to determine whether this inside-out growth pattern is common or an anomaly in the early universe. Dr. Tacc Hella explains, "Of course, this is only one galaxy, so we need to know what other galaxies at the time were doing. We're now analyzing similar data from other galaxies. By looking at different galaxies across cosmic time, we may be able to reconstruct the growth cycle and demonstrate how galaxies grow to their eventual size today." Initial comparisons have revealed a diverse array of galactic structures in the early universe. Some galaxies appear to be growing more uniformly, while others show signs of mergers or interactions with neighboring galaxies. This diversity suggests that multiple pathways of galaxy evolution were already in play less than a billion years after the Big Bang. One particularly interesting comparison is with so-called red nuggets, compact, massive galaxies that have been observed in slightly later epochs of the universe. These galaxies are thought to be the progenitors of today's massive elliptical galaxies. The newly observed galaxy, with its dense core, may represent an even earlier stage in the formation of these cosmic behemoths. Another point of comparison is with local dwarf galaxies in the present-day universe. Despite the vast difference in cosmic time, some of these nearby small galaxies show similar patterns of active star formation in their outer regions. This raises intriguing questions about the universality of certain galactic growth processes across cosmic time. The Webb Telescope's observations of this early galaxy provide a crucial test for theoretical models of galaxy formation and evolution. For decades, astronomers have relied on computer simulations to model how galaxies might have formed and grown in the early universe. Now, for the first time, we have observational data to compare against these models. William Baker, the PhD student involved in the study, emphasizes this point. It's incredibly exciting to see how well some of our models align with Webb's observations. But it's even more thrilling when we spot discrepancies. These are the areas that push our understanding forward. One area where observations and models seem to align is in the prediction of inside-out growth. Many simulations had suggested that early galaxies would form dense cores first, followed by extended periods of star formation in their outer regions. The newly observed galaxy provides strong evidence for this scenario. However, the rapid growth rate observed in this galaxy has surprised some theorists. Many models predicted a more gradual buildup of stellar mass in the early universe. The observed galaxy's ability to double its mass in the outskirts every 10 million years suggests that early star formation may have been more efficient than previously thought. Another area of interest is the galaxy's chemical composition. Theoretical models have long predicted that the first galaxies would be composed primarily of hydrogen and helium, with heavier elements, metals, in astronomical terms, being rare. Spectroscopic data from Webb will allow astronomers to test these predictions and refine our understanding of chemical enrichment in the early universe. The discovery of this rapidly growing, structurally mature galaxy in the early universe has far-reaching implications for our understanding of cosmic evolution. It suggests that the processes shaping galaxies were already well established less than a billion years after the Big Bang, challenging some of our assumptions about the timescales of cosmic structure formation. One of the most significant implications is the potential need to revise our models of dark matter behavior in the early universe. The compact, dense nature of this galaxy suggests that dark matter halos may have collapsed and concentrated more quickly than some models predict. This could have profound implications for our understanding of both galaxy formation and the nature of dark matter itself. The observation also sheds light on the process of cosmic reionization, the period when the first stars and galaxies ionized the neutral hydrogen that permeated the early universe. The high star formation rate observed in this galaxy suggests that similar objects could have played a crucial role in driving reionization, which is thought to have occurred around the same cosmic epoch. Furthermore, This discovery provides new insights into the relationship between galaxies and their central supermassive black holes. Many astronomers believe that galaxies and their central black holes co-evolve, but it's unclear how this relationship is established. The presence of a dense core in this early galaxy raises questions about whether a supermassive black hole might already be present, and how it might be influencing the galaxy's growth. The rapid growth observed in this galaxy also has implications for our understanding of how galaxies acquire their gas. It suggests that efficient mechanisms for funneling gas from the cosmic web into galaxies must have been in place very early in cosmic history. This could lead to new investigations into the dynamics of gas flows in the early universe. The recent discoveries about inside-out galaxy growth in the early universe significantly challenge our previous understanding of cosmic evolution. Observations from the James Webb Space Telescope have uncovered a galaxy that appears surprisingly mature for its age, sparking profound questions about the formation and evolution of galaxies like our Milky Way over billions of years. The implications of this discovery extend far beyond a single galaxy. They suggest that the processes governing galaxy formation were already in place much earlier than previously thought, reshaping our models of cosmic history. As researchers continue to analyze more data from Webb, we can expect even more revelations about the conditions of the early universe and the mechanisms that drove the formation of galaxies. Thank you for joining us on this fascinating journey into the depths of space and time. If you enjoyed this video and want to stay updated on future explorations of the cosmos, be sure to subscribe to our channel. Your support helps us bring more incredible discoveries to light. Feel free to share your thoughts in the comments below. What excites you most about these findings? Until next time, keep looking up at the stars, because there's always more to discover in our ever-expanding universe. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. In the universe, countless stars twinkle in the darkness. But among them, the smallest and most numerous hold a secret. M-dwarf stars, often overlooked, might just be the key to unlocking the greatest mystery of all: are we alone in the universe? Recent discoveries have shaken the scientific community. Planets orbiting these tiny stars, once thought to be cosmic wastelands, may actually harbor the ingredients for life. It's a revelation that's turning our understanding of habitability on its head. Today, we'll be talking about rocky planets orbiting small stars and their potential for stable atmospheres, because why not? The implications are staggering. Could these worlds, bathed in the dim light of red dwarfs, be oases of life in the cosmic desert? But there's a twist. The very stars that give these planets a chance at life also threaten to strip away their atmospheres. It's a cosmic tug-of-war with the highest stakes imaginable. As we peer through the lens of the James Webb Space Telescope, we're on the brink of answering questions that have haunted humanity for centuries. Are these distant worlds barren rocks, or could they be teeming with alien life? Let's dive deep into this subject of rocky planets orbiting small stars and uncover the truth hiding in plain sight among the stars. The quest for extraterrestrial life has entered an exhilarating new phase with the launch of NASA's James Webb Space Telescope in late 2021. This powerful observatory has revolutionized our ability to detect potential signs of life on exoplanets, those distant worlds orbiting stars beyond our solar system. As we peer into the cosmic depths, our attention has been drawn to a particular class of celestial bodies, rocky planets circling low-mass stars known as M-dwarfs. M-dwarfs, also called red dwarfs, are the most common type of star in the universe, making up about 75% of all stars in the Milky Way. Their abundance and longevity make them prime targets in the search for habitable worlds. Among these, the TRAPPIST-1 system has emerged as a focal point of scientific interest. Located a mere 40 light-years away, this M-dwarf star hosts 7 Earth-sized planets, several of which orbit within the star's habitable zone. The TRAPPIST-1 system represents a unique opportunity for astronomers and astrobiologists. Its proximity to Earth and the nature of its planets make it an ideal laboratory for studying potential extraterrestrial environments. The James Webb Space Telescope's advanced instruments allow us to analyze the atmospheres of these distant worlds with unprecedented detail, searching for chemical signatures that could indicate the presence of life. As we continue to explore systems like TRAPPIST-1, we edge closer to answering one of humanity's most profound questions: are we alone in the universe? The search for life beyond Earth has captured human imagination for centuries, and now, with cutting-edge technology at our disposal, we stand on the brink of potentially groundbreaking discovery. Previous research had cast doubt on the habitability of planets orbiting M-dwarfs like TRAPPIST-1. Scientists were concerned that intense ultraviolet radiation from these stars would strip away surface water, leaving planets desiccated and potentially covered in reactive oxygen that could inhibit the chemistry necessary for life to emerge. This scenario painted a bleak picture for the prospects of life on worlds circling these small, red stars. However, a groundbreaking study has shed new light on this cosmic conundrum, offering a glimmer of hope for alien life enthusiasts. The research suggests that a specific sequence of events during the evolution of certain rocky planets orbiting M-dwarfs could result in the formation of stable atmospheres over time. This finding challenges the previously held notion that all planets around M-dwarfs are doomed to be barren, irradiated worlds. The study reveals a complex interplay between a planet's interior, its atmosphere, and the radiation from its host star. While it's true that M-dwarfs emit intense UV radiation, especially during their early, more active phases, some planets may have mechanisms to counteract this hostile environment. The key lies in the planet's ability to outgas and retain certain atmospheric components, creating a protective shield against the star's harsh radiation. Joshua Christensen-Totten, a lead researcher, emphasizes the significance of this finding. One of the most intriguing questions right now in exoplanet astronomy is, can rocky planets orbiting M-dwarf stars maintain atmospheres that could support life? Our findings give reason to expect that some of these planets do have atmospheres, which significantly enhances the chances that these common planetary systems could support life. This research opens up new avenues for exploration and challenges us to reconsider our understanding of planetary habitability. It suggests that the story of life in the universe may be more resilient and adaptable than we previously thought, potentially thriving in environments we once considered impossible. The James Webb Space Telescope, JWST, plays a crucial role in the search for potentially habitable exoplanets, particularly those orbiting M-dwarf stars. Its advanced capabilities allow for detailed observations of planetary systems around these small, cool stars. Early data from JWST has provided insights into the atmospheres of rocky planets orbiting M-dwarfs. For instance, observations of the TRAPPIST-1 system, located 40 light-years away, suggest that some of its innermost planets likely lack substantial atmospheres. The telescope has successfully measured heat radiating from TRAPPIST-1c, ruling out a thick carbon dioxide atmosphere for this rocky world. However, the telescope faces challenges in characterizing planets in the Goldilocks zone, the region where conditions might be suitable for liquid water. These temperate planets, slightly farther from their host star, are of particular interest in the search for potentially habitable worlds. Observing them requires significant telescope time, with new research suggesting it could take hundreds of hours of JWST observing time to detect atmospheres on these planets with a high degree of certainty. The telescope's sensitivity to infrared light makes it ideal for studying cooler, more distant objects. This capability has led to discoveries beyond just exoplanets, including the identification of brown dwarfs, objects too small to become stars but larger than planets, in the Orion Nebula. JWST's observations are crucial in understanding the diversity of planetary systems and the potential for life beyond Earth. As more data is collected, scientists hope to gain a clearer picture of the atmospheric conditions on various types of exoplanets, particularly those orbiting M-dwarf stars. The University of Washington-led study employed sophisticated computer models to simulate the evolution of rocky planets orbiting M-dwarf stars. These simulations tracked the planet's development from their initial molten state through hundreds of millions of years of cooling and solidification. The results provided fascinating insights into the potential for stable atmospheres on these worlds. The models revealed a complex interplay between a planet's interior, its atmosphere, and the radiation from its host star. During the early stages of planetary evolution, hydrogen and other light gases readily escaped into space due to the intense heat and radiation from the young M-dwarf star. However, for planets located farther from their host star, where temperatures are more moderate, a different process unfolded. In these cooler regions, hydrogen reacted with oxygen and iron in the planet's interior, producing water and heavier gases. This chemical process resulted in the formation of an atmosphere that the simulations suggest could remain stable over long periods. The heavier gases produced by these reactions are less likely to escape the planet's gravity, contributing to the atmosphere's longevity. Furthermore, the study revealed an intriguing phenomenon for planets within the Goldilocks zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface. In these cases, water tends to rain out of the atmosphere relatively quickly. This process makes it less likely for water to escape into space, potentially creating conditions favorable for retaining this essential ingredient for life. The simulations also considered the long-term effects of stellar radiation and planetary cooling. As the M-dwarf star settles into its main sequence phase and its radiation output stabilizes, the planet's atmosphere continues to evolve. The interplay between atmospheric escape, chemical reactions, and the planet's internal heat creates a dynamic system that can, under the right conditions, lead to a stable, potentially life-supporting environment. These findings challenge previous assumptions about the habitability of planets orbiting M-dwarf stars and open up new avenues for exploration in the search for potentially habitable worlds beyond our solar system. The findings from recent studies on rocky planets orbiting M-dwarf stars have significant implications for the ongoing search for life beyond our solar system. While the James Webb Space Telescope, JWST, has not yet definitively determined whether more temperate planets like those in the TRAPPIST-1 system have atmospheres, the potential for their existence is tantalizing. If these planets do possess atmospheres, it could indicate the presence of surface liquid water and climates potentially conducive to life. However, the search for habitable worlds around M-dwarf stars faces several challenges. Recent evidence suggests that planets orbiting these stars may be uninhabitable due to the mismatch between their liquid water and ultraviolet habitability zones. Life requires both liquid water and the right amount of ultraviolet radiation, but for M-dwarf stars, these zones often do not overlap. Additionally, the intense radiation during the pre-main sequence phase of M-dwarfs could strip away water from these planets or trap it on their cold night sides. Despite these challenges, some researchers remain optimistic. Studies have shown that subglacial melting could extend the habitable region around M-dwarf stars. These subglacial oceans, protected by ice layers from energetic stellar radiation, could provide safe environments for the evolution of organic life over extended periods. The JWST and future extremely large ground-based telescopes will play crucial roles in characterizing the atmospheres of potentially habitable exoplanets. However, as Christensen points out, we will only be able to study a small number of habitable zone rocky planets' atmospheres in the near future. This limitation underscores the importance of carefully selecting targets and investing significant telescope time in these observations. Recent observations of planets in the TRAPPIST-1 system have provided mixed results. While TRAPPIST-1b appears to lack a significant atmosphere, studies of TRAPPIST-1c suggest it may have only a tenuous atmosphere with minimal carbon dioxide. These findings highlight the complexity of planetary evolution around M-dwarf stars and the need for continued, detailed observations. As we continue to explore space and search for signs of life beyond Earth, studies like these bring us closer to answering the profound question of whether we are alone in the universe. The rocky worlds orbiting small stars may indeed hold the keys to unlocking this cosmic mystery. However, the search requires patience, advanced technology, and a nuanced understanding of the various factors that contribute to planetary habitability. The quest for life in the cosmos remains one of the most exciting and challenging endeavors in modern science, driving technological innovations and pushing the boundaries of our understanding of the universe. As we explore the fascinating potential of rocky planets orbiting small stars, it becomes clear that the universe is full of surprises. The research surrounding M-dwarfs and their planets challenges our previous notions of habitability and opens the door to new possibilities. These worlds, once dismissed as inhospitable, may actually possess stable atmospheres capable of supporting life. The implications of these findings are profound. With the James Webb Space Telescope leading the charge, we stand on the brink of potentially groundbreaking discoveries. Each observation could bring us closer to answering one of humanity's most enduring questions: are we alone in the cosmos? The tantalizing prospect that life might exist on these distant planets ignites our curiosity and fuels our desire to explore further. Thank you for joining us on this journey through the intriguing realm of rocky planets and their potential for life. If you found this topic as captivating as we do, be sure to hit that subscribe button and turn on notifications so you won't miss any future explorations into the mysteries of the universe. Your support helps us continue to bring you exciting content about the wonders of space and science. We'd love to hear your thoughts. What do you think about the possibility of life on these rocky worlds? Share your ideas in the comments below. Until next time, keep looking up at the stars, because who knows what incredible discoveries await us just beyond our reach. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. In the cold, shadowy depths of our solar system, a small moon clings to its orbit around a gas giant. From afar, it might seem like just another lifeless rock drifting in the void. But this moon, Io, hides a secret so explosive, it shatters all expectations of what's possible in the outer reaches of our cosmic neighborhood. Io isn't just any moon. It's a volcanic powerhouse, an inferno in miniature. No larger than our own moon, its surface is constantly reshaped by hundreds of raging volcanoes, spewing molten rock and sulfur into space. A landscape of chaos, burning brighter and angrier than anything else we've discovered. But here's where it gets strange. Recent findings from NASA's Juno mission have uncovered something shocking deep within Io's fiery core. Something that could upend everything we thought we knew, not just about Io, but about volcanic worlds scattered across the universe. What did Juno uncover? What lies beneath Io's churning, molten crust? The answers could rewrite the story of not just this moon, but the very nature of volcanic worlds. And yet, they raise even bigger, darker questions. Questions we may not be ready to face. Let's dive into the burning mystery of Io. Or perhaps, we should ask, will we survive what we uncover? In the shadow of Jupiter, where the gas giant's massive presence looms large, lies Io, a moon that captivates scientists and astronomers alike with its astonishing volcanic activity. This celestial body, slightly smaller than Earth's moon, is not just another rocky satellite, it is a vibrant world alive with fire and fury. Io is home to an estimated 400 active volcanoes, making it the most volcanically active body in our solar system, a title it has held for decades. The surface of Io is a mesmerizing tapestry of colors, ranging from deep reds and yellows to ashen grays, all created by the relentless eruptions that reshape its landscape. These eruptions are not sporadic, they are continuous and dynamic, with volcanic plumes that can reach heights of over 300 kilometers, 186 miles, into space. This constant activity results in a surface that is ever-changing, with fresh lava flows and sulfur deposits painting a vivid picture of geological chaos. The discovery of Io's volcanic nature dates back to 1979 when Linda Morabito, an imaging scientist at NASA's Jet Propulsion Laboratory, first identified a volcanic plume in images captured by Voyager 1. This groundbreaking observation ignited a wave of curiosity among planetary scientists who began to question how such intense volcanic activity could occur on a moon so far from the Sun. Io's unique geology can be attributed to its position within the Jovian system. It orbits extremely close to Jupiter, about 262,000 kilometers, 163,000 miles, and experiences immense gravitational forces that stretch and compress its interior. This tidal heating is a key factor in powering its volcanoes and is a phenomenon that has intrigued scientists for years. As we delve deeper into the mysteries of Io, we uncover not just a moon but a dynamic world that challenges our understanding of geology and planetary science. The study of Io is not merely academic, it provides insights into the processes that shape not only our solar system but potentially other planetary systems throughout the galaxy. NASA's Juno spacecraft has been instrumental in unlocking the secrets of Jupiter and its moons since its arrival in 2016. Among its many achievements, Juno has provided unprecedented insights into Io's geological activity through close flybys that have revealed critical data about this fiery moon's internal structure. In December 2023 and February 2024, Juno made two remarkable flybys of Io, coming within just 930 miles, 1,500 kilometers, of its tumultuous surface. During these close encounters, Juno utilized its advanced instruments to gather high-precision data on Io's gravity field, a feat that has led to groundbreaking revelations about how this moon functions beneath its volatile exterior. For decades, scientists have pondered whether the volcanoes on Io are fed by a global ocean of magma or if they draw from localized magma chambers hidden beneath the surface. The findings from Juno suggest that each volcano is likely powered by its own individual chamber of molten rock rather than being connected to a single vast reservoir beneath the moon's crust. This revelation solves a mystery that has perplexed planetary scientists for over 4 decades. Scott Bolton, Juno's principal investigator at the Southwest Research Institute in San Antonio, emphasized the significance of this discovery. Since Morabito's discovery in 1979, planetary scientists have wondered how these volcanoes were fed from beneath the surface. Juno's close flybys provided crucial data that allowed researchers to measure how gravity affects the spacecraft's acceleration as it passed over Io's varied terrain. The implications of these findings extend beyond just understanding Io. They challenge existing models about other celestial bodies as well. The knowledge gained from Juno may influence our understanding of other moons like Enceladus and Europa, both known for their potential subsurface oceans, and even exoplanets orbiting distant stars. As we continue to analyze Juno's data, we are reminded that exploration often leads us to unexpected revelations about our universe. Each new piece of information helps us construct a more comprehensive picture of how celestial bodies evolve and interact with their environments. At the heart of Io's violent geology lies an intricate dance between gravitational forces and tidal flexing, an interplay that shapes not only this moon but also our understanding of planetary dynamics across the solar system. Io orbits Jupiter at an astonishing speed, completing a revolution every 42.5 hours due to its close proximity to the gas giant. This rapid orbit subjects it to intense gravitational forces that vary dramatically as it moves through its elliptical path around Jupiter. The result is tidal flexing, a phenomenon where the gravitational pull stretches and compresses the moon's interior. This constant flexing generates immense heat through friction within Io's interior layers, effectively melting portions of its rocky mantle and creating pockets of magma that fuel its numerous volcanoes. As Scott Bolton explains, this constant flexing creates immense energy which literally melts portions of Io's interior. The energy produced by these tidal forces is so significant that it rivals some processes seen on Earth during tectonic activities. Juno's analysis revealed that if there were indeed a global magma ocean beneath Io's surface, we would expect to see much larger signatures from tidal deformation than what was observed during the flybys. Instead, what emerged was evidence supporting a more rigid structure dominated by localized magma chambers, each volcano drawing from its own source rather than relying on a shared reservoir. Understanding these tidal forces not only enhances our knowledge about Io but also provides valuable insights into other celestial bodies experiencing similar gravitational interactions, such as Saturn's moon Enceladus or even exoplanets orbiting distant stars where tidal heating could play a crucial role in their geological activity. As we continue to study these phenomena through missions like Juno, we gain a deeper appreciation for the complex processes at play within our solar system and beyond, reminding us that even distant worlds can share fundamental characteristics. The discoveries about Io's internal structure are shaking the foundation of planetary science, offering profound implications for our understanding of celestial mechanics both within our solar system and beyond. This fiery moon forces us to reconsider long-held assumptions about geological activity on other moons and planets, particularly those influenced by intense gravitational dynamics. Juno's findings challenge the prevailing belief that global magma oceans are essential to sustain volcanism on celestial bodies, like Enceladus or Europa. Instead, Io suggests an alternative: localized mechanisms may drive volcanic activity, bypassing the need for expansive subsurface reservoirs. This revelation widens the scope of possibilities for geological processes across a range of environments, hinting that volcanic activity may be far more diverse and widespread than previously thought. With this new lens, scientists are encouraged to re-examine other moons and even exoplanets with fresh curiosity. Could hidden geological features, fueled by localized processes, be at work on worlds we've barely begun to understand? If Io has taught us anything, it's that the universe rarely conforms to our expectations. But the implications go deeper than volcanic activity alone. Io's unique characteristics force us to rethink planetary formation itself, how celestial bodies evolve under varying conditions shaped by their proximity to massive planets or stars. Worlds that share similar origins may take vastly different paths, creating environments as unexpected as Io's volatile surface. As researchers continue to analyze Juno's data alongside observations from missions like Galileo and New Horizons, it becomes clear that exploration often leads to more questions than answers. Every discovery peels back another layer of mystery, challenging established norms and driving us toward uncharted scientific territory. Studying Io doesn't just teach us about a distant moon, it also offers a window into Earth's own geological processes, reminding us that the forces shaping our planet are part of a much larger cosmic story. And as we uncover these insights, they propel us toward the next frontier, seeking to understand the unknown worlds that lie beyond our solar system. Io's fiery revelations are just the beginning, inviting us to imagine what other secrets the universe has yet to reveal. As NASA's Juno mission continues its groundbreaking exploration of Jupiter, the scientific community waits in growing anticipation for what lies ahead, not just for the gas giant itself but also for its captivating moons, particularly Io, a fiery enigma pulsating with untold secrets. Since entering Jupiter's orbit in July 2016, Juno has conducted dozens of flybys, each adding invaluable pieces to the puzzle of this distant world. On November 24, 2024, the spacecraft completed its 66th science flyby, offering fresh insights into Jupiter's swirling atmospheric phenomena while also collecting data from its neighboring satellites, including the ever-turbulent Io. Now, all eyes are on December 27, when Juno's next close approach is set to pierce deeper into the mysteries surrounding Jupiter's cloud tops and Io's volatile surface. With every flyby, the mission inches closer to unraveling the intricate connections between the gas giant and its dynamic moons. Scientists are optimistic that the data gathered will reveal new patterns, shedding light on Io's molten heart and the gravitational forces that drive its geological chaos. But Juno's journey is only the beginning. Future missions dedicated solely to Io are already sparking excitement. These missions could venture closer than ever before, probing Io's volatile geology and exploring its fiery surface to unlock the mechanics of volcanism across different celestial environments. Such studies may even hold clues about the potential for life on icy worlds in the far reaches of our solar system. The deeper we dig into Io's fiery depths, the more it reminds us of the boundless nature of human curiosity. Every discovery Juno makes propels us closer to understanding not just Io, but the broader tapestry of life and evolution across the cosmos. And yet, with each new answer comes an even bigger question: what else is Io hiding beneath its tumultuous surface? The revelations to come may not only reshape our view of this moon but could forever alter our understanding of what's possible in the universe. The countdown to December 27 has begun, and with it, the hope of unearthing truths that might surpass our wildest imaginations. Io is truly a remarkable moon, showcasing a level of volcanic activity that challenges our understanding of celestial bodies. The insights gained from NASA's Juno mission have illuminated the unique processes that drive Io's eruptions, revealing that each volcano is powered by its own localized magma chamber. This discovery not only reshapes our perception of Io but also prompts us to rethink the geological dynamics of other moons and planets throughout the universe. The implications of these findings extend far beyond Io itself, offering new perspectives on how tidal forces can influence geological activity in various environments. As scientists continue to analyze data from Juno and other missions, we can anticipate even more exciting revelations about the nature of volcanic worlds, both within our solar system and beyond. Thank you for watching this deep dive into Jupiter's volcanic moon. If you enjoyed this exploration, please give us a thumbs up and share it with fellow space enthusiasts. Don't forget to subscribe for more fascinating content about the mysteries of our universe. Your support enables us to continue bringing you the latest discoveries and insights from the frontiers of science. Until next time, keep your curiosity alive and continue to look up at the wonders of the cosmos. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. A discovery has shaken the very foundations of astronomy, a revelation so baffling it might rewrite the story of the cosmos itself. Massive galaxies, as enormous as the Milky Way, were already thriving when the universe was just a cosmic infant. Hidden for billions of years behind veils of dust, these ancient behemoths, glowing with an eerie red light, have finally been unmasked by the James Webb Space Telescope. Dubbed red monsters, these galaxies are unlike anything scientists expected to find. They're defying every rule in the book, forming stars at a pace so frenzied it shatters our understanding of how galaxies grow. It's like stumbling upon a galactic factory, one that seems impossibly advanced for its time, a place where stars are born faster than physics says they should be. Today, we'll be talking about these mysterious red monster galaxies because why not? They've thrown everything we thought we knew about galactic evolution into chaos. How did they grow so big, so fast? What secrets might they still be hiding? And what does their existence mean for our models of the universe? Let's dive deep into this subject and unravel the cosmic mystery that has astronomers worldwide questioning everything. Astronomers have made a remarkable discovery that reshapes our understanding of the early universe. Thanks to the advanced capabilities of the James Webb Space Telescope, JWST, researchers have identified 3 ultramassive galaxies, each nearly as massive as our own Milky Way, existing within the first billion years after the Big Bang. These extraordinary galaxies, affectionately dubbed red monsters due to their high dust content and distinctive reddish appearance, are challenging long-held beliefs about galaxy formation and evolution. These galaxies are not merely enormous, they are anomalies in almost every way. Packed with stars, gas, and dust, the red monsters push the boundaries of what astronomers thought was possible in such a young universe. Previously, it was assumed that galaxies this massive took much longer to assemble. Their discovery hints that either our understanding of galaxy formation is incomplete or that the conditions of the early universe allowed for unexpectedly rapid growth. The FRESCO program, using the JWST's NIRCam GRISM spectrograph, has been pivotal in revealing these cosmic giants. By analyzing the light that has traveled billions of years to reach us, astronomers can pinpoint not only their distances but also their stellar masses. These measurements provide a snapshot of a universe still in its infancy, a time when galaxies were forming and evolving at breakneck speed. What makes the red monsters even more extraordinary is their star-forming efficiency. Unlike the galaxies observed at later times or those of similar mass but smaller size, these cosmic titans are producing stars at nearly twice the rate. Such prolific star formation challenges current models, which suggest that galaxies in this era should have been less efficient at converting gas into stars due to turbulent conditions and limited resources. Instead, these red monsters seem to thrive in their environments, assembling stars at an unprecedented pace and scale. The implications of this discovery are profound. It forces astronomers to rethink the timelines of galaxy growth and the physical processes that govern it. How did these galaxies accumulate so much mass so quickly? Were the conditions of the early universe vastly different from what we've modeled? Could this mean there are even more such behemoths waiting to be found? As we gaze through the lens of the James Webb Space Telescope, we are not just seeing these distant red monsters, we are witnessing the rewriting of cosmic history. This discovery is a testament to the power of modern astronomy and a reminder that the universe is always more surprising and complex than we imagine. The discovery of these red monsters has deeply challenged the scientific community, prompting researchers to rethink long-standing theories about galaxy formation and evolution. For decades, the dominant model suggested that galaxies emerged gradually, forming within large halos of dark matter. Gas would slowly collect in these halos, cooling and condensing over time to form stars. This process was thought to be relatively slow and methodical, with only about 20% of the available gas converting into stars. However, the existence of these ultramassive galaxies in the early universe rewrites this narrative. Observed less than a billion years after the Big Bang, these red monsters demonstrate that star formation in this early epoch was far more dynamic and efficient than previously believed. Instead of forming slowly, these galaxies appear to have grown explosively, converting gas into stars at rates that far surpass current expectations. Dr. Mengyuan Xiao, who led this revolutionary study, explains the significance of the findings. Our discoveries are reshaping our understanding of galaxy formation in the early universe. With the help of the James Webb Space Telescope, JWST, astronomers can now peer through thick layers of cosmic dust that previously obscured these massive galaxies. Their immense size and rapid star formation were hidden from earlier instruments, but JWST's advanced capabilities have brought them into focus for the first time. This discovery raises important questions about the conditions that allowed such rapid galaxy growth in the universe's infancy. Were these galaxies located in regions with exceptionally dense gas supplies? Did their environments foster unique interactions, such as galaxy mergers or enhanced gravitational forces, that accelerated their evolution? Or is there a missing piece in our understanding of how galaxies formed under the extreme conditions of the early universe? The implications extend far beyond these individual galaxies. Their existence suggests that the processes governing galaxy formation may have been more diverse and complex than previously thought. This newfound knowledge pushes the boundaries of astrophysical research, inviting scientists to explore what other cosmic phenomena may have gone unnoticed. One thing is clear: discoveries like these are reshaping how we view the earliest epochs of the universe and its remarkable capacity for complexity and growth. The identification of these red monsters showcases the extraordinary capabilities of modern astronomical instruments, particularly the James Webb Space Telescope, JWST. This cutting-edge observatory has transformed how we study the cosmos, providing an unparalleled view of the most distant and ancient structures in the universe. Its ability to peer through dense cosmic dust and capture light that has traveled billions of years is revolutionizing our understanding of the early universe. Programs like FRESCO, designed to explore emission-line galaxies, demonstrate the precision and scope of JWST's technology. By focusing on galaxies that existed within the first billion years after the Big Bang, the FRESCO program has allowed researchers to systematically analyze these ancient structures. With JWST's NIR-CAM-GRISM spectrograph, astronomers can accurately determine distances and stellar masses, providing a clearer picture of galaxy formation during the universe's infancy. This meticulous approach has unlocked a treasure trove of data, shedding light on phenomena that were previously beyond our reach. Pascal Oesch, an associate professor involved in this groundbreaking observation program, underscores the significance of this advancement. The instrument on board allows us to identify and study galaxy growth over time. JWST's ability to track the development of galaxies across epochs offers a unique glimpse into the processes that shape the cosmos. By observing galaxies at various stages of their evolution, scientists can reconstruct the conditions and mechanisms that gave rise to these massive cosmic structures. The discovery of the red monsters is a testament to the transformative power of modern astronomy. These galaxies, hidden behind thick layers of dust, were virtually invisible to previous telescopes. Now, with JWST's advanced instruments, researchers can study not only their existence but also their composition, star-forming efficiency, and the environments in which they thrived. This deeper level of exploration is rewriting our understanding of how galaxies grew under the extreme conditions of the early universe. Beyond the technical achievements, the power of modern astronomy lies in its ability to connect us with the distant past. Each discovery, such as the red monsters, brings us closer to answering profound questions about the origins of the universe. It reveals a cosmos that is more complex, dynamic, and awe-inspiring than we ever imagined, pushing the boundaries of human knowledge and curiosity. The JWST's success is not just a technological triumph but a bold step forward in humanity's quest to understand. The discovery of the red monsters presents astronomers with intriguing challenges and opens new avenues for refining our understanding of galaxy formation in the early universe. These ultramassive galaxies, with their astonishing rate of star formation, introduce a new dimension to what's known as the too many, too massive problem, a dilemma in early galaxy formation theories. While these findings don't directly contradict established cosmological models, they undeniably raise important questions about the processes that allowed certain massive galaxies to evolve so quickly in the early universe. For years, cosmological models have suggested that galaxies formed in a gradual manner, their growth largely driven by dark matter halos that helped gather gas. However, the discovery of these red monsters forces astronomers to reconsider how such massive galaxies could form and develop so rapidly. These galaxies, forming stars at much higher rates than expected, challenge the slow and steady growth that had been the basis of galaxy evolution theories. This discovery indicates that certain processes, possibly yet unidentified, must have contributed to their unprecedented pace of star formation. Dr. David Elbaz, a prominent astrophysicist, points out that before the advent of the James Webb Space Telescope, the study of these dust-obscured giants was nearly impossible. The thick dust clouds surrounding these galaxies rendered them invisible to traditional optical telescopes, which rely on visible light to capture cosmic data. The optical attenuation caused by this dust obscured much of the light emitted by the stars within these galaxies, preventing researchers from fully understanding their structure and star-forming efficiency. This revelation underscores the pivotal role infrared astronomy plays in unlocking hidden aspects of our cosmic history. JWST's infrared capabilities enable astronomers to see through the dust that has long concealed the true nature of these ancient galaxies, revealing details about their star formation and evolution that were previously inaccessible. By observing the universe in infrared wavelengths, scientists can study objects that are otherwise invisible, thereby expanding our knowledge about how galaxies form, evolve, and interact across cosmic time scales. As astronomers continue to investigate these red monsters, they will likely find that our current models of galaxy formation need significant refinement. These discoveries challenge our assumptions and push the boundaries of our understanding, prompting the scientific community to rethink not just how galaxies grow, but also what cosmic processes were at play during the earliest, most dynamic periods of the universe's history. The future of cosmology, it seems, will be written in the infrared, as we continue to uncover the hidden wonders of the cosmos. As we step into this exciting new era of cosmology, it's clear that the discovery of the red monsters is just the beginning of a much larger journey into the mysteries of the early universe. These ultramassive galaxies, with their rapid star formation and unique characteristics, represent only a glimpse of what lies ahead as we continue to push the boundaries of space exploration. With future observations using the James Webb Space Telescope, JWST, and other advanced instruments like ALMA, Atacama Large Millimeter Array, astronomers are poised to uncover even deeper insights into these galaxies, potentially revealing even larger and more diverse samples from the universe's infancy. The red monsters have already opened a window into the conditions that prevailed during some of the earliest epochs of our universe's history. However, this is just the start. As JWST and other next-generation observatories continue to collect data, researchers are likely to uncover additional galaxies that challenge our understanding of how cosmic structures emerged. With each new discovery, we will gain a clearer understanding of the complex processes that shaped galaxies in the first few billion years after the Big Bang. Dr. Mengyuan Xiao, one of the leading scientists in this field, expresses his excitement about the future of early universe studies. As we study these galaxies more deeply, they will offer new insights into conditions that shaped our universe. His words reflect the enthusiasm within the scientific community as researchers look ahead to the wealth of information that will be unlocked through continued exploration. These findings will not only provide answers to long-standing questions but also raise new ones, pushing the field of cosmology into exciting, uncharted territory. The discoveries surrounding these red monsters signal a shift in our understanding of how galaxies form, evolve, and interact. This shift is more than just a change in scientific theories, it's a call to action for astronomers, astrophysicists, and researchers to think in new ways and explore the unknown. The cosmos is vast, and as we continue to explore deeper into space, we will uncover more cosmic wonders, each one building upon the last. This journey into the depths of the early universe challenges established paradigms and invites a sense of awe at the magnitude of what we have yet to learn. With every new discovery, we move closer to unraveling the mysteries of our cosmic origins, a pursuit that not only answers profound questions but also fuels the human curiosity to understand the universe in its most distant, earliest moments. The future of early universe studies is bright, and with each new exploration, we edge closer to a deeper, more comprehensive understanding of the cosmos. The discovery of the red monster galaxies has profound implications for our understanding of the early universe. These ultramassive galaxies, forming stars at extraordinary rates, challenge long-held theories about galaxy formation and evolution. Their existence suggests that the processes governing galaxy formation were far more dynamic and efficient than previously imagined. The significance of these findings goes well beyond just these three galaxies. They push us to rethink current models of cosmic evolution and explore new mechanisms that could explain how such massive structures emerged so soon after the Big Bang. With ongoing data from the James Webb Space Telescope and other cutting-edge instruments, further revelations are certain to expand our knowledge of the cosmos. If you found this exploration of the red monsters intriguing, be sure to subscribe to our channel for more updates on the latest astronomical discoveries. Your support allows us to continue bringing exciting content to you. Don't forget to tap the notification bell so you never miss an update. We're eager to hear your thoughts on this topic. What are your views on the implications of these findings? Drop your insights in the comments below. Until next time, keep your eyes on the stars and stay curious about the universe. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. Today we'll be talking about the mind-bending exoplanet TRAPPIST-1b because why not? Nestled 40 light-years from Earth, this rocky world has been hiding secrets that could revolutionize our understanding of planetary science. Picture a distant planet that defies everything astronomers thought they knew, a world where nothing is as it seems. Recent measurements from the James Webb Space Telescope, JWST, have thrown scientific communities into a state of complete bewilderment. TRAPPIST-1b, once written off as a barren, dead rock, is now teasing the possibility of something extraordinary. Its surface lacks the scars of constant cosmic bombardment, no signs of weathering or cratering typically seen on such planets. Could it be volcanic activity? A concealed atmosphere? Or something we've never even imagined? What's even stranger is the rock itself. Observations suggest it might be impossibly young, potentially as little as 1,000 years old, despite the planet existing for billions of years. How can this be? What processes could explain such an anomaly? Scientists have spent 290 hours of JWST observation time studying this enigmatic world, but answers remain elusive. TRAPPIST-1b's mysteries deepen with every revelation, leaving experts to question the very foundations of planetary science. This isn't just another exoplanet, it's a puzzle that refuses to be solved. As speculation grows and the data pours in, one question looms larger than all the rest: what unimaginable secret is TRAPPIST-1b protecting? Let's dive into the enigma of TRAPPIST-1b and uncover the details that have scientists holding their breath. TRAPPIST-1b, an intriguing exoplanet located 40 light-years from Earth, has long been regarded as a dark, rocky world devoid of an atmosphere. However, recent findings from the James Webb Space Telescope, JWST, are challenging this perception. Observations have revealed a lack of weathering on its surface, signs typically associated with cosmic radiation and meteorite impacts, suggesting that TRAPPIST-1b might be geologically active. This possibility hints at the existence of an atmosphere, potentially rich in carbon dioxide, which could alter our understanding of this enigmatic planet. The TRAPPIST-1 system itself is remarkable, hosting 7 Earth-like planets, 3 of which orbit within the habitable zone where liquid water might exist. TRAPPIST-1b, though closest to its star and outside this zone, remains a subject of intense study due to its unique characteristics. Its proximity to Earth has made it an excellent target for detailed observation, and the JWST has allocated a substantial 290 hours across 10 research programs to unravel the mysteries of these planets. Led by Elsa Ducrot from the Commissariat aux Énergies Atomiques, CEA, in Paris, with contributions from researchers at the Max Planck Institute for Astronomy, MPIA, a groundbreaking study focused on TRAPPIST-1b utilized the JWST's MIRI, mid-infrared imager, to measure the planet's thermal infrared radiation. These measurements provide critical insights into its atmospheric composition, or lack thereof, and surface conditions. The potential discovery of a carbon dioxide-rich atmosphere on TRAPPIST-1b would significantly impact our understanding of planetary evolution around low-mass stars. Such findings could pave the way for re-evaluating the habitability of planets previously dismissed as barren. While TRAPPIST-1b may not host life, the ongoing research highlights the complexity of planetary systems and the importance of modern technology like the JWST in reshaping our cosmic perspective. The findings from the James Webb Space Telescope reveal something astonishing about TRAPPIST-1b. The rock on its surface appears shockingly young, estimated to be no more than 1,000 years old. This revelation directly contradicts the planet's age, which spans billions of years. Such a disparity suggests the presence of dramatic geological processes reshaping the surface, possibly through extreme volcanism or active plate tectonics. These processes could be responsible for the lack of weathering typically expected on a planet exposed to constant cosmic radiation and impacts from space debris. The notion of ongoing geological activity raises tantalizing questions about what might be occurring beneath TRAPPIST-1b's surface. One possibility is that the planet has retained residual heat from its formation, much like Earth. This retained heat could drive a dynamic interior, fueling processes capable of renewing the surface. Another compelling explanation involves the tidal forces exerted by TRAPPIST-1b's central star and its neighboring planets. The gravitational push and pull could create internal friction, generating heat similar to the intense volcanic activity seen on Jupiter's moon Io. What makes this discovery even more intriguing is its implications for the planet's atmosphere, or lack thereof. Geological activity could potentially support an atmosphere, perhaps one rich in carbon dioxide, providing further evidence that TRAPPIST-1b is far from a dead, barren rock. Alternatively, the activity might point to processes so extreme that they strip the atmosphere away as quickly as it forms. Each new piece of data deepens the mystery surrounding TRAPPIST-1b. What drives these processes? How can a planet's surface remain so young in a system billions of years old? These questions remain unanswered, keeping scientists captivated as they dig deeper into the planet's enigmatic story. TRAPPIST-1b's case highlights both the promise and the limits of current astronomical tools. The Haze hypothesis, though intriguing, remains a less likely scenario. Yet, the possibility cannot be entirely ruled out. As scientists continue to refine their methods, the question lingers: could TRAPPIST-1b's secrets be hidden within an atmosphere that defies expectations? TRAPPIST-1b's case highlights both the promise and the limits of current astronomical tools. The Haze hypothesis, though intriguing, remains a less likely scenario. Yet, the possibility cannot be entirely ruled out. As scientists continue to refine their methods, the question lingers: could TRAPPIST-1b's secrets be hidden within an atmosphere that defies expectations? Studying exoplanets like TRAPPIST-1b presents immense challenges, particularly due to the thin atmospheres of rocky planets compared to the thick, easily measurable atmospheres of gas giants. While gas giants produce strong atmospheric signatures, rocky planets like TRAPPIST-1b are far more elusive, requiring innovative techniques and lengthy observation periods. The recent JWST observations of TRAPPIST-1b lasted nearly 48 hours, but even this was insufficient to draw definitive conclusions about the presence or composition of its atmosphere. Astronomers primarily rely on transit spectroscopy to study exoplanet atmospheres. This method involves measuring the dimming of starlight as a planet passes in front of its host star, with specific wavelengths of light being absorbed by atmospheric gases. By analyzing these patterns, researchers can infer the existence and composition of a planet's atmosphere. However, TRAPPIST-1, a cool red dwarf star, complicates this process. Red dwarfs are notoriously active, with large star spots and intense flares that can distort or obscure the measurements. These stellar characteristics pose a significant hurdle to extracting clear data. To overcome these obstacles, researchers have increasingly turned to secondary eclipse measurements as an alternative. This method focuses on observing the thermal infrared light emitted by a planet's heated dayside as it disappears behind its host star. By analyzing the infrared radiation emitted just before and after the planet is eclipsed, astronomers can glean critical information about its surface properties and any potential atmosphere. While this approach avoids the interference caused by the star's activity, it comes with its own challenges. Secondary eclipse measurements are far more time-consuming than transit spectroscopy and require precise alignment of the planetary system to our line of sight. For TRAPPIST-1, the slight inclination of the planetary orbits to our vantage point has proven advantageous. This orientation allows all 7 planets in the system to transit the star, causing measurable dimming and enabling astronomers to gather invaluable data. With TRAPPIST-1b specifically, the JWST's thermal infrared observations have revealed intriguing details about its dayside. However, the limitations of these measurements highlight the need for longer observation times and more refined techniques. Recognizing these challenges, NASA has recently approved an ambitious program called Rocky Worlds, which dedicates 500 hours of JWST observation time to studying the atmospheres of rocky planets around nearby low-mass stars. This program aims to push the boundaries of what we can learn about planets like TRAPPIST-1b. By leveraging secondary eclipse measurements and other advanced techniques, researchers hope to unlock the secrets of these enigmatic worlds, even in the face of red dwarf star activity. TRAPPIST-1b exemplifies both the promise and the difficulty of studying rocky exoplanets. The data gathered so far has expanded our understanding of its surface and atmospheric potential, yet the full picture remains tantalizingly out of reach. Future efforts under programs like Rocky Worlds offer hope for breakthroughs, inching us closer to unraveling the mysteries of planets like TRAPPIST-1b. The study of TRAPPIST-1b offers a glimpse into the rapidly advancing field of exoplanet research, where new technology like the JWST is transforming our ability to probe distant worlds. This ongoing exploration not only challenges long-standing theories but also reveals the immense complexity of determining whether planets beyond our solar system could harbor life or possess unique geological features. TRAPPIST-1b, in particular, has become a focal point for testing innovative methods and pushing the limits of current observational techniques. One of the most promising avenues for understanding TRAPPIST-1b lies in recording its complete orbital phases, a technique designed to provide a more comprehensive view of the planet's characteristics. By capturing data across its entire orbit, including its dark night side when it passes in front of the star and its bright day side as it emerges before being eclipsed, astronomers can create a phase curve that reveals variations in brightness. This phase curve, in turn, offers critical insights into the planet's surface temperature distribution and, potentially, the presence of an atmosphere. The presence or absence of an atmosphere can be inferred by analyzing how heat is distributed across the planet. An atmosphere would act as a medium for heat transport, evening out temperature differences between the scorching day side and the frigid night side. Without an atmosphere, the temperature transition between these two hemispheres would be abrupt and dramatic. Initial measurements of TRAPPIST-1b's thermal distribution have already been carried out, and the results will play a pivotal role in determining the planet's atmospheric status. These efforts underline the broader implications of studying TRAPPIST-1b. The planet serves as a case study for rocky exoplanets orbiting red dwarf stars, a class of planets that could prove crucial in the search for extraterrestrial life. However, the challenges involved, from deciphering subtle temperature gradients to mitigating the effects of stellar activity, highlight just how much remains unknown. Future observations, including those under ambitious programs like NASA's Rocky Worlds, aim to refine our understanding of TRAPPIST-1b. The insights gained will not only shed light on this intriguing exoplanet but also inform the search for atmospheres and habitability on other rocky worlds. As astronomers continue their quest, TRAPPIST-1b stands as a vivid reminder of both the progress and the challenges in the study of distant planets. Each new observation builds on the last, inching closer to answering fundamental questions about the nature of these alien worlds, and, perhaps one day, their potential to support life. TRAPPIST-1b continues to captivate us, revealing a wealth of surprises that push the boundaries of our understanding of rocky exoplanets. Thanks to the groundbreaking observations of the James Webb Space Telescope, this distant world has proven to be more enigmatic than anticipated, reshaping how we think about planetary atmospheres and geological activity. The hints of dynamic processes, whether through potential volcanic activity, heat-driven surface renewal, or a hazy carbon dioxide-rich atmosphere, underscore the intricate and often unpredictable nature of these alien worlds. Such discoveries highlight the incredible complexity of exoplanetary science and reinforce the need for ongoing exploration. TRAPPIST-1b reminds us that the universe is a treasure trove of the unexpected, constantly challenging our assumptions about how planets form, evolve, and interact with their environments. With every breakthrough, we move one step closer to answering the profound questions about whether life could exist elsewhere and what conditions make a planet truly unique. As we look ahead to future observations, particularly through ambitious programs like NASA's Rocky Worlds, we find ourselves on the cusp of even more extraordinary discoveries. These initiatives promise to deepen our understanding of TRAPPIST-1b and other rocky exoplanets, offering a glimpse into their hidden stories and untapped mysteries. Thank you for joining us on this journey through the fascinating world of TRAPPIST-1b. If you're as intrigued as we are by the search for life and the secrets of distant planets, be sure to subscribe to our channel and turn on notifications to stay updated on the latest cosmic revelations. Your curiosity fuels the exploration of the universe, reminding us all to keep looking up, wondering, and exploring the infinite possibilities that lie beyond our sky. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.